Okay, question 1 from the AAHL exam is here, which is the same question as question 2 from the AASL exam. So the following recording is my work solution from question 2 from the AASL exam. The nth term of an arithmetic sequence is given by UN is equal to 15 minus 3n. Part A asks us to state the value of the first term U1. Right, okay, so let's highlight or underline this expression that we're given at the top for the nth term. And yeah, let's highlight this bit, so U1. So for this, what we're going to do is we're going to substitute in sub n equals 1 into the equation UN is equal to 15 minus 3n. Right, and so that's going to give us UN, U1, because n is equal to 1. U1 is equal to 15 minus 3 times by 1, which just equals 15 minus 3, which is going to be 12. All right, and so then, yeah, we can put over here, therefore, U1 is equal to 12. Lovely. Okay, let's move on to part B. So, given that the nth term of the sequence is negative 33, we've got to find the value of n. Okay, so we're told that UN is equal to negative 33 and got to backtrack. So essentially doing the opposite to what we did in part A. We've been given what the value of U or the nth term, and we've got to, yeah, unravel it essentially. So what we're going to do is say let UN equal negative 33 and rearrange for n. Okay, so we're going to let, UN equal negative 33. So negative 33 is equal to 15 minus 3n. Okay, so from here, what I'm going to do is, first of all, I will, let's subtract 15 from both sides. All right, and then that's going to give me negative 48 over here is equal to negative 3n. And then next, I'm going to divide by negative 3. And then that's going to give me what we got. 16 is equal to n. All right, and then that is our answer there. Okay, so n is equal to 16. All right, let's move on to part C. Okay, find the common difference, D. Okay, so to help us out with this one, we're going to bring over, or I'm going to write down the nth term formula, which is given in your formula booklet for an arithmetic sequence. It's good to get familiar with this one, though it is given to you in that formula booklet. And it is as follows. UN is equal to U1 plus n minus 1 multiplied by D. Okay, so we don't know D, but there are a few things that we do know, okay? We know that U1 is equal to, as we found at the top, 12, okay? Equally, we know that U16 is equal to negative 33. So I could plug in n is equal to 16 into this formula that we've got here and sort of unravel it to find D. I hope you don't mind the term unravel. Rearrange perhaps would be more familiar. So yeah, let's go and do that. So substitute n is equal to 16. And so we'll have U16 is equal to, in fact, let's write this in. Let's write this in. We'll go, this is going to give us U, in fact, we'll go into blue. U16 is equal to U1 plus 16 minus 1 multiplied by D. Okay, so now plug in the values that we know. So we know U16 is negative 33. We know U1 is 12. We can sort of solve 16 minus 1, which is going to be 15. So 15D. All right. And so then from here, my first protocol will be to subtract 12 from both sides. Let's do that. So bring this down here and say subtract 12. And so negative 33 subtract 12 is going to give me negative 45. So negative 45 is equal to 15D. It's not overly accurate, my arrow there, but anyway, okay. And then my next step is going to be to divide both sides by 15, and then that will get rid of the 15 from the right hand side, from the common difference from the D, and so that's going to give me negative 45 over 15 is equal to D, and then we can conclude, therefore, D is equal to negative 3. Question 2 from the AAHL exam is here, which is identical to question 3 from the AASL exam. So the following recording is my work solution from question 3 of the IB AASL exam. Question 3. Consider any 3 consecutive integers, n-1, n, and n+1. Part A asks, prove that the sum of these 3 integers is always divisible by 3. Okay, cool. So let's highlight our integers, our 3 consecutive ones. These guys, and we're going to prove that the sum of these integers is okay. So always divisible by 3. We'll highlight. Okay, and the sum. All right. So first of all, let's go and sum up these integers and see what we find. So the sum is going to be n-1 plus n plus n plus 1. Okay, which would be the same as if we just got rid of all the brackets. We don't, brackets there are to just show that they're sort of separate integers, but we don't need them, so we can sort of get rid of all of them here. And now we can kind of see that we end up having 3 positive n's, a negative 1, and a positive 1. So essentially this negative 1 and this positive 1, they're just going to cancel each other out. And we get this expression equal to 3n. All right. Now, when we divide 3n by 3, we get n, right? And we were told here I can cancel those out as well, cancel the 3's. And so we got 3n divided by 3 is equal to n. And we were also told that at the start they were integers. And so we can sort of conclude, therefore, the sum of 3 consecutive, let's see if I can fit that in there, consecutive integers is always divisible by 3. Okay, lovely. Yeah, and that would suffice for part A. Okay, moving on to part B. Prove that the sum of the squares of these 3 integers, so let's take away, first we'll take sum of the squares of these 3 integers is never divisible by 3. Never divisible by 3. Okay, all right. So first of all, we're going to have to, find the sum of these squares. All right. So this is going to be n minus 1 squared plus n squared plus n plus 1 squared. Right. Now I'm going to go off into a bit of a tangent here and just talk about these n minus 1 squared and n plus 1 squared. It's quite a common error to just square the two terms that are within the brackets. So you go n squared, and then negative 1 squared would be 1, so just call it n squared plus 1. And unfortunately, that would be wrong. Okay, so the best way to attack these questions is to write out the bracket twice. And so that's going to be n minus 1 squared. Okay, and now if we do that, what have I done? We're going to get, this is going to be equal to n squared minus 2n, all right, then plus 1. Okay, and then equally, if we do that for n plus 1 squared, that's going to equal n plus 1 multiplied by n plus 1. And now if we expand out these brackets, we're going to get n squared plus 2n plus 1. Okay, cool. Now let's put these on the side there, yeah. All right, so now if we go and add all these up, the expressions that we've got n squared minus 2n plus 1 plus n squared plus n squared plus 2n plus 1. Okay, so if we go through here, we can see that this negative 2n is going to basically cancel out this positive 2n at the far end down there. And so we have n squared here, n squared here, n squared here. Okay, so they're all going to add up together to give us 3n squared. And this one is going to add onto this one here and give us plus 2. All right, so the sum of the squares are equal to 3n squared plus 2. And what I'm going to do is let's bring it down this first line and show that. Okay, so therefore, we'll put a little therefore sign on the left-hand side here. The sum of the squares come to this. Now, when we go about dividing this expression here, 3n squared by 3, we end up getting this. So 3n squared plus 2 divided by 3 is the same as writing 3n squared divided by 3 plus 2/3. And so once again, we can cancel out these 3's here, and we get n squared plus 2/3. All right, and so we've shown that when we divide the sum of these squares here, we are left with when we add the sum of the squares here and then divide it by 3, we are left with n squared plus 2/3, all right, which will never be an integer. And so we can go on and say, therefore, n squared is always an integer. And 2/3 is not, hence the sum of the squares is never divisible by 3. All right, and then that is our answer to question 3. Beg your pardon, question 3. Question 3 from the AAHL exam is here, which you'll see is very similar to question 4 from the AASL exam, with the only exception being part D, as you can see here, which is added on to the end. And so the following recording is my answer to question 4 from the AASL exam. And then after that, you'll have a recording of me running through the answer to part D. Question 4. A function f is defined by fx is equal to 2x minus 1 over x plus 1, where x is an element of real numbers and x cannot equal -1. Part A asks, the graph of y equals fx has a vertical asymptote and a horizontal asymptote. Write down the equation of part 1, the vertical asymptote, and part 2, the horizontal asymptote. Okay, so for the vertical asymptote, this will always be in the form of x equals a number. And you'll find quite often that this is given in the first line of the question, okay? Which here we're told we've got x cannot equal -1. Now, the reason why x can't equal -1 is if we were to put that x equals -1 into the denominator here, we would get 0. And we can't divide by 0 because then our function is undefined. Okay, so that is a bit of a hard and fast rule that you can take. So the vertical asymptote here is going to be x is equal to -1. We will copy this down and we'll do all the working. It's on the next page here, so we'll do it down there. Now, the horizontal asymptote for these functions, which they're called rational functions, and I'll give you their form as well. So the form of rational functions are ax plus b over cx plus d. All right, and so that's essentially what we have for f here. And we will write the horizontal asymptote as the limit as x tends to positive and negative infinity of fx. Now, I know that might not mean an awful lot yet, but I will explain that as we go down. All right, so let me get rid of this here. Let's come down. So I'll write a bit of a note in blue, so you wouldn't have to write the blue bit here in your exam, but the red bit that I write will be the kind of the answer. All right, the answer plus the working. All right, so for any rational function, fx is equal to, I think I just copied here, yeah, ax plus b, it's made a little small, ax plus b over cx plus d. Our vertical asymptote is x is equal to d over c. Sorry, big pardon, negative d over c. Okay, and you'll see that this is essentially the value of x that makes the denominator equal to 0. And so equally, so for the horizontal asymptote, is y is equal to negative a, sorry, what am I doing? Not negative, just a over c. So effectively the coefficients of x divided by each other. So yeah, a over c. So if we were to write our answers in here, so first of all, we're asked to put in the vertical asymptote. So let's just write this. We'll go vertical asymptote is style red, right? X is equal to -1. And yeah, as I said earlier, quite often this is given to you in the first sentence of the question, of these types of question. So yeah, look out for that. And then now this idea here, okay, so the horizontal asymptote. So now you can just use this formula here and you'll see that it's 2 and 1. I do want to sort of illustrate this idea or expand on this idea of the limit as x tends to positive or negative infinity. So if we write that down here, limit as x tends to positive and negative infinity of, what do we have, 2x minus 1 over x plus 1. What we end up getting is 2 lots of plus and minus infinity minus 1 over plus or minus infinity plus 1. Okay, now the minus 1 on the top and the plus 1 on the bottom will, considering we're working with infinity here, will do very little to the value of this limit. Okay, so specifically all we're going to be looking at is the coefficients of x, or the coefficients of positive and negative infinity. And so what we're going to say is that this is equal to 2. Okay, because effectively this cancels out with this, right? And the -1 plus 1, they basically make no effect. All right, so then therefore what we're going to say, therefore the horizontal asymptote, I'm just going to copy this. Oh, what have I done? Brought the y over. Let's make that into red, is y is equal to 2. All right, and so there is the answer for part A. And this idea here for the limit, the reason why I wanted to expand on that idea is this is going to help quite a bit for this next part, so part B, okay, for when we get to sketching the graph. All right, so yeah, going up to part B, we are asked, on the set of axes below, sketch the graph of y equals fx. I'm just going to put equals to 2 here as well, so we got that. Okay, so how about so first of all, let's draw in the asymptotes we have, okay, and we'll do that with a dotted line. So here is, oh, that's not perfect, is it? But we'll line it up, and so that is the equation of the vertical asymptote there. Yeah, I don't think this photocopy was taken straight, but that's all right. Okay, cool. So we got that there, and then also the equation of the horizontal asymptote is going to be y is equal to 2. Right, and so there we have the two asymptotes drawn. Okay. Though for this question here, we're going to need, so we're saying on your sketch, clearly indicate the asymptotes. So we've got that here. The asymptotes, but equally, and the position of any points of intersection with the axes. We'll just get intersection with the axes. We'll also indicate there. All right. So let's go back down to our working page, and we'll talk a little bit about the how to find the x-intercept and the y-intercept for these rational functions. So I'm going to copy this for any rational function idea here. Let's bring this down. So for any rational function, the x-intercept is going to be as follows, okay, is -b over a comma 0. And hold on, let's bring this over to here, make it a little smaller. And the y-intercept is going to be when x is equal to 0, and then b over d. Okay, and there you have it. And you can also, if you forget this, the x-intercept is when the function or y is equal to 0, so you can go through and just sort of solve that. Okay, and the y-intercept is when x is equal to 0. And then just expanding a little bit on the idea of the x-intercept when the function is equal to 0. When you're trying to find that, all you're concerned about is making the numerator equal to 0 because it doesn't matter what you divide 0 by, it's always 0. So yeah, 0 divided by anything is always going to be equal to 0. That's what we'd be concerned about there. Okay, cool. So then in terms of our question here, we got x. The x-intercept here is going to be not -0.5. It's going to be, what do we have? So yeah, -1/2, beg your pardon, yeah. No, sorry, because we've already got -1, so it's -1, so yeah, just a half, comma 0, and the y-intercept is going to be equal to 0, comma, and then b over d, which is -1 over d, which was 1, which is just -1. All right, cool. So there we have our x-intercept and y-intercept. Let's mark that on a graph here. So we got our x-intercept here of 1/2, comma 0. Okay, and then equally the y-intercept, which was 0, comma -1. And I'm just going to zoom in a little bit here. Move this guy to there and move this guy slightly over to there. Okay, cool. So there we have now the x-intercept, y-intercept, and also our asymptotes drawn. Let's just mark those. We'll say this is where y is equal to 2, and this is where x is equal to -1, for our vertical asymptote. Now, in our part B, we talked about the limits. Sorry, part part 2 of question A. We talked about the limits as x tends to positive and negative infinity. All right, and we found that our function tends towards 2. Okay, so it goes towards this 2 idea. So as x tends towards positive infinity, our line tends towards this line y equals 2, but never quite touches it. Okay, so it never touches it, but it tends towards that value. Okay, equally, we know as x tends towards negative infinity, so going this way, our line is going to come down, it's going to tend towards this line here. That wasn't very good. Tend towards y is equal to 2, but it won't ever touch that line. Okay, so that gives us a little bit of an indication, or a bit of help as to the shape of our graph. And so we know on the positive side of x, okay, as x increases there, we want our line going towards the line of y equals 2, and equally on the other side, we want our line when it goes to, as x tends to negative infinity, we want our graph tending towards this line of y is equal to 2. All right, and so then when we think about that, this bottom bit is going to, so we've got to go through our y-intercept and x-intercept. And so we'll get a line somewhat similar to this here. Okay, and then as x increases, this line gets closer and closer to y is equal to 2, but never touches it. Equally, as y gets, as y tends towards negative infinity, or as x tends towards -1, all right, we know that our graph, our function tends towards negative infinity. Okay, and then now we go up to the top, and so we also know that on this negative side, okay, so around here, we need our graph tending towards y is equal to 2, but never quite touching it. All right, and so then we get this idea here, where we come through and we go out like this. All right, and then there we have our graph, okay, of fx, of y is equal to fx. And yeah, that should suffice for part B. Okay, let's move on. Part C asks, hence solve the inequality. 0 is less than 2x minus 1 over x plus 1, which is less than 2. Okay, so if we look at our graph here, we need to find when our function fx, because this expression here is just fx. So going up to our graph, we've got to find when is the value of fx between 0 and 2. Okay, and we can specifically see that that is from this point onwards here. Okay, yeah, so from the x-intercept onwards, all right? And we know that since we found the limit, that fx will never it'll never get to y is equal to 2. So simply the answer, or the solving this inequality, is just x needs to be more than a half, right? And so we can write that down here and say 4, 0, and then we'll say, what's it, 2x plus 1. Oh, wait, it was minus 1, wasn't it? 2x minus 1 over x plus 1 less than 2. X must always be more than a half. And there is the answer to part C. Okay, on to part D. Solve the inequality. Here, this inequality here. And so we'll come down and I've copied it down here, and I've also brought our graph. And so it's quite easy to overthink this one here, because it probably looks more complicated than it really is. So what we're going to think is, if we have when x or 4x is greater than 0, all right, our expression here, 2 multiplied by the x minus 1 over the absolute value of, I want to go straight from here, x, not brackets, sorry, absolute value, plus 1. Now this is just going to equal effectively fx, which was 2x minus 1 over x plus 1. All right, and so that's pretty straightforward. Okay, so that's just going to be, so if I sort of redo our graph in purple for this function here, the absolute value stuff in it, that's just going to be identical for when x is greater than 0. So anything to the right of the y-axis. Okay, so now when we think of that, let's have a look at when x is negative. All right, so for x is less than 0. All right, so then this idea here, so 2 multiplied by x, the absolute value of x, minus 1 over x plus 1. Now, this is going to be effectively, so we're considering only negative values of x, okay? So, and what this absolute value sign is, makes these negative values positive, right? So what we could effectively do is just multiply it by -1. Okay, so we could just put a negative x into our function. And so then you can say that this is going to equal 2 multiplied by negative x minus 1 over negative x plus 1. So you can think about it like that, or equally, you can sort of have the idea of, well, if x is equal to -1/2, then we're going to have to just find the corresponding value for when x is 1/2, okay? Because that's what we're going to be effectively plugging into our function. And so if we zoom in onto our function here on our graph, well, when x is 1/2 here, y is equal to 0. All right, so that means when x is equal to -1/2 for our new function, y is also going to have to be 0. So we end up seeing that we effectively just get a, pardon my drawing, I know it's not perfect, I was never an artist. But you can see that we end up just getting a reflection in the y-axis here. All right, so that's effectively all we get. So, and you could also note that this thing here, this looks like f of -x, which means therefore reflect in y-axis. All right, you should probably remember that from your transformations section or idea. Right, and so then now we have a graph of the inequality here, and we can kind of tell, okay, well, when is this inequality between 0 and 2? Well, it's always going to be below 2, because we still have that horizontal asymptote of y is equal to 2. But we have sort of two parts now that are greater than 0. We have sort of, if I highlight in green, we've got this sort of section down to here, and then this section up here. All right. So to answer our question, this inequality is satisfied for x is greater than a half and x is less than negative a half. All right. And then that is the answer to part D. Question 4 from the AAHL exam is here, which you'll see is identical to question 5 from the AASL exam, which is here. So the following recording is my work solution from the question 5 from the AASL exam. Question 5. Find the least positive value of x for which cos of x over 2 plus pi over 3 is equal to 1 over the square root of 2. Okay, cool. Let's highlight this idea of the least positive value of x. And then, yeah, I've got a big expression there. Right, so first things first, with this question, I'm going to say let theta equal x over 2 plus pi over 3. And then therefore that means I can say there cos theta is equal to 1 over the square root of 2. Yeah, do that again. Okay, so if you're not familiar with these, with your exact value triangles, I would encourage you to sort of commit them to memory. Here I've got one here. Here is an exact value triangle, which is effectively a right-angled isosceles triangle, where the two sides that are the same length are length 1. And then if you run Pythagoras theorem, you'll find that the hypotenuse is the square root of 2. And then from here, you'll be able to find the exact values of cos, sine, tan of 45 degrees or pi over 4. Okay, so here is the triangle here. So therefore, we can say that theta here will have to equal pi over 4. All right, since pi over 4 here, the adjacent side is 1, and the hypotenuse is root 2, and cos of theta is equal to the adjacent side divided by the hypotenuse. Okay, so therefore we'll put theta is equal to pi over 4. Okay, so moving on from this, now let's so now we've got theta is equal to this and theta is equal to this. So we can say there then that pi over 4 is equal to x over 2 plus pi over 3. And if we rearrange this for x over here, let's just go across here. So x is going to equal pi over 4 minus pi over 3, and I've forgotten to times by 2, but we'll bring that in. But here we've run into a bit of a problem, since already, before I even times this by 2, what's in the bracket here? Pi over 4 minus pi over 3. This here, this is less than 0, okay? Which is a problem, okay? Because we need to find the least positive value of x. All right, so we'll note that and say this is less than 0. Okay, so therefore theta being equal to pi over 4 isn't valid. Well, it would satisfy this equation here, but it's not the least positive value of x. Oh, sorry, of theta. And then this would give us a negative value of x, which would satisfy the equation, but doesn't answer the question because we need the least positive value of x. So here I'm going to give you a bit of a cos theta rule, or you can sort of figure this out from the cos graph if you draw it out. But a bit of a hard and fast rule is So I'll write this in blue. Cos theta is equal to cos 2 pi minus theta, or if we were in degrees, we could put cos 360 minus theta. And so then therefore, okay, if theta is equal to pi over 4 here, then another possible value for theta would be 2 pi minus pi over 4, which is going to give us 7 pi over 4. Okay, because this would turn into 8 pi over 4. There we go, 8 pi minus pi. And so yeah, we get 7 pi over 4. All right, cool. So then now let's move on and let's try and use 7 pi over 4 for our theta. Okay, so we'll take this expression here that we had for x. All right, let's substitute in 7 pi over 4 instead of 7 pi over 4 instead of pi over 4. So we'll just, where's my rubber? Get rid of this, lob in 7 pi over 4. Okay, and then now we're going to have to do a bit of working. So let's say this is going to equal 2 lots of. Now to get a common denominator here, we can go with the standard with 12. Okay, so we're going to go with 21 pi. All right, because to get 4, the denominator of 4, to become 12, we have to times it by 3. That means we have to times its numerator by 3 as well. So we get 21 pi. Then for the pi over 3, we have to times the 3 by 4 to make it 12. That means we have to times the pi, this pi here, by 4. Okay, so then we go minus 4 pi. And we had a common denominator of 12. All right, sweet. And so then this is going to give us 17 pi 12. Yeah, good. Sweet. Okay, cool. And then that is going to equal 34 pi over 12. And then to finish up, we have a common factor between these two of 2. So we can change that to 17. Change this to 6. Divide them both by 2. And so our final answer is x is equal to 17 pi over 6. Okay, and now that is the least positive value of x that satisfies this equation up here. All right, just to expand quickly on the magic triangle, exact value triangle. Okay, so here, this one here, this is the isosceles right-angled triangle. Okay, where the two sides of the same are length of 1. You can then use Pythagoras to find out that the hypotenuse will be square root of 2. And given it's an isosceles triangle, we know that the base angles have to be the same. So, and we know the angles of the triangle add up to 180. So they both have to be pi over 4 or 45 degrees. Question 5 from the AAHL exam is here, which is identical to question 6 from the AASL exam, which is here. And so the following solution, work solution, is my recording from the AASL exam for question 6. Question 6. Consider the binomial expansion x plus 1 to the power of 7 equals x to the power of 7 plus ax to the power of 6 plus bx to the power of 5 plus 35x to the power of 4 plus ... plus 1, where x can't equal 0 and a and b are part of positive integers. And part A asks, show that b is equal to 21. All right, cool. So let's look at what we need here. So obviously we're going to show that b is equal to 21. And we can see from our expansion that b is the coefficient of our x to the power of 5 term. All right, so we're going to need to go to our formula booklet and use the formulas that we have for the binomial theorem, which is over here, and we can see down here. So let's just copy what we've got there, and we'll bring these over. Nice. Okay, cool. And so the main thing that you're going to want to sort of pay attention to here is the general term here. All right, so this idea. So NCR, NCR is equal to A to the power of n minus r multiplied by B to the power of r. All right, and in our circumstance here, x is A and 1 is B. Okay, so if we apply that idea to bx to the power of 5, all right, we can sort of say, well, n is going to be equal to 7, a is equal to x, and b is equal to 1. And we got to do a bit of thinking to find out what r is, but unfortunately it's not too tricky. So if we're trying to find the x to the power of 5 term, x to the power of 5 term, which is, funnily enough, equal to b, all right, which is going to equal n, so NCR, and n is 7. All right, we'll put r down here for now. 7CR multiplied by x to the power of 7 minus r, and multiplied by 1 to the power of r. Okay? And so now we got to think, what sort of value of r do we need to make the power of x equal to 5? All right? And when we sort of go through this, we can sort of conclude that it's going to be 2, all right? Because 7 minus 2 is equal to 5. Right, so therefore r is equal to 2, and we can sort of bring our working down. Let's grab this, bring it down. Let's change r's to 2, and then another 2. All right, cool. And so we know that 1 to the power of anything is just going to stay as 1. We know that this has now become x to the power of 5, so that's happy. So we can conclude that b is going to equal 7c2. And actually, to be technically correct here, how about we put in bx to the power of 5? In fact, we'll go back it up a little bit. We'll put bx to the power of 5, x to the power of 5, and we'll include that down here as well. I don't think you'd necessarily be marked wrong if you didn't put this in, but this is just to help with understanding, okay? So then we can go over here. So therefore, b is going to equal 7c2. All right, cool. And there we go. And we can even cancel out these two terms, and 1 to the power of anything is just going to be 1. All right, cool. So now we've got b is equal to 7c2. And so now we're going to have to move on to the NCR formula, or this formula down here, where we have n factorial divided by r factorial multiplied by n minus r factorial. Okay, so if we apply this, so then we can come down here, we'll say b is going to be equal to 7 factorial over 2 factorial multiplied by 7 minus 2 factorial. All right, so there's a few things we can kind of do to make our life a little bit easier here. So if you're not familiar with what factorial means, so 7 factorial, for example, is 7 times 6 times 4, sorry, 7 times 6 times 5 times 4 times 3 times 2 times 1, all right? And so 2 factorial is 2 times 1, right? So what we can do here is we can clean this up a little bit, and let's say we call it 2 factorial multiplied by 5 factorial, right? Because that's going to be 7 minus 2. Now, what I can do to this numerator, this 7 factorial, is I can change it to being 7 times 6 times by 5 factorial, okay? Because 5 factorial is just going to be 5 times 4 times 3 times 2 times 1, so that's the equivalent of 7 factorial. Then I can divide this now by the same thing, 2 factorial multiplied by 5 factorial, and now I have an opportunity to cancel out my 5 factorials, okay? And so that makes our life a little bit easier, and so now we've got 7 times 6 divided by 2 factorial. We already know that 2 factorial is just going to be 2, because that's just 2 times 1. So we get this is equal to 42 over 2, and then we can sort of finish out by saying therefore, or B is equal to 21. And that is the answer to part A. On to part B. The third term in the expansion is the mean of the second term and the fourth term in the expansion. So I'm going to use a green highlighter for this question, okay? So the third term in the expansion, the mean, right, of the second term and the fourth term. Okay, so if we go through this and sort of have a think of what we got. So the third term is what we've just found, bx to the power of 5, and we're told that b is 21. So we can say, so this is 21x to the power of 5. The second term is ax to the power of 6, and we don't know the value of a yet. So we're probably going to, we're going to have to find that out. And the fourth term is 35x to the power of 4. Okay, so our first port of call will be to find out what ax to the power, or what the value of a is, okay? And the way we're going to do that is a very similar process as the part A in terms of finding the R value that we need in order to have x to the power of 5. But in this case, we need to find the R value that's going to give us x to the power of 6, okay? And so if we look back up at this bit here, all right, let's actually use a bit of a highlighter. If we look at this bit here, we can think, what value of R do we need in order to get x to the power of 6? And so specifically, that would be looking at the 7 minus R bit, and that's going to be 1, okay? We need R to equal 1, because then we're going to get 7 minus 1, which will then give us x to the power of 6. So let's have a look at that. So we can let's bring this down here, and we'll say ax to the power of 6 is going to equal 7c1 multiplied by x to the power of, 7 minus 1, but let's put in 6, and then multiplied by 1 to the power of 1, which is always just going to be 1, all right? And so off to the right here, we can say, therefore, a is equal to 7c1. Now, you can go through the formula here, all right, and lob this in, where we're going to get, 7 factorial divided by 1 factorial multiplied by n minus r factorial, which is going to be 6 factorial. In fact, we'll put this in. But a bit of a hard and fast rule that you can sort of remember is any number C1 is going to be that number, okay? So, for instance, so here we're going to get, actually, let's write it in. So 7 factorial over 1 factorial multiplied by 7 times, 7 minus 1 factorial, which we should put in 6 factorial. Okay, and then using a similar idea as before, we could say that this is 7 times by, in fact, let's bring it down to a new line. Yeah, we'll bring all of this down to a new line. Let's bring this down, done. Okay, and so then this is going to be the same as doing 7 times 6 factorial. We know 1's just going to be 1 factorial is just 1 times itself, or just, it's just 1, so that's 1. And so we can say divided by 6 factorial, we can do our cancelling, and then we get left with just 7, okay? So therefore, a is equal to 7, so that's our happy days. All right, so now we know that we've got the second term is 7x to the power of 6, fourth term is 35x to the power of 4, and third term is what we were actually told what b was. So even if you couldn't sort of do the full answer for part A, you can still then at least attempt part B, which is quite nice. All right, so our second term, so this one here, so 7x to the power of, beg your pardon, no, our third term is the mean of the second and fourth term. So 21x to the power of 5 is equal to 7x to the power of 6 plus 35x to the power of 4 divided by 2. Okay, so that's the way to calculate the mean of two numbers or two terms, or you add them together and then you divide by the the number of terms that you have, which we have 2 here, so we divide by 2. All right, and cool. And so here we have an expression where we're going to have to do some manipulation, sort of figure out what we'll do from here. So first things first, what I think is a good protocol is just times both sides by 2, and so that's going to give me 42 x to the power of 5 here is going to give me 7x to the power of 6. I'm going to end up going on to the next page here, but that shouldn't be a worry. Okay, so here we have a couple terms. So what we could also do now is divide both sides, we could divide all sides or everything here by x to the power of 4, which would leave me with 42x multiplied by 7x squared plus 35. Okay, and then now if we bring everything over to one side, and actually what we'll do is bring this over to the left a bit, make it a bit smaller. Yeah. Make this a bit smaller, and then we can hopefully work off to the right. Yeah, that'll do. All right, cool. And so it's just putting a line down here. Well, we can bring all this to one side, yeah? And we can get 7x squared minus 42x. So I am subtracting 42x from both sides here. If I subtract 42x from this side, it's going to equal 0. And we get plus 35. And then this is equal to 0. All right, and so now I have a quadratic for which I could just lob into the quadratic formula. So we can simplify it and then attempt to factorize. Now, I don't recommend spending too much time in trying to factorize something, because sometimes it can't be done. But yeah, always sort of briefly think to yourself, can I factorize this? Because it is more efficient than sort of plugging it into the quadratic formula. All right, and so from here we get the idea of we divide all of our terms here by 7. We'll get x squared, and we're also, so we're dividing the whole equation, so the left-hand side and the right-hand side by 7. And if we divide 0 by 7, we just get left with 0, okay? So 7x squared divided by 7 is x squared minus 6x, and then plus 5 is equal to 0. All right, and so then from here, what we can do is attempt to factorize. And so because we have a positive c value, all right, actually first things first, what we're going to look at is the coefficient of x squared. 9 times out of 10, that is going to be just 1, right, which is quite nice. So then we can sort of start our factorization with just x and x, okay? And so now we look at our c term, right? Our c term is positive, which means the sign within our brackets, they're going to have to be the same, all right? If it was negative, then that means they're going to have to be different, right? And so now I say the same, that means they can be plus and plus or minus minus. And you may ask why, how do you figure that out, or where do you go to from here? And the place we go to is the beta, okay? And we see that that's negative, all right? So we're going to need minus minus, all right? And we think now, what are factors of 5 that add up to 6, all right? And it's quite fortunate 5 is a prime number. It only has 5 in itself, so 1 in itself, and that 1 plus 5 is 6. That's quite fortunate. So we get x minus 5 and x minus 1 is equal to 0, okay? And so therefore, the possible values of x are x is equal to 5 and x is equal to 1, right? And then there is the answer to part B. And question 6. Question 6. The function f is defined by fx is equal to x times the square root of 1 minus x squared, where x lies between -1 and +1. The graph of y equals fx is shown below. right? And show that part A asks, show that f is an odd function. Okay, so for this, we're going to have to use the definition of an odd function, which I'll write down for you, which is f of negative x is equal to negative fx, right? And additionally, we can sort of see that it's fx does look like an odd function because an odd function has rotational symmetry about the origin. So here, of 180 degrees or pi radians. So we can see that if we sort of copy our graph, let's paste an image here, we can see if we rotate it around half, we have the same function. So it certainly looks like an odd function, but we're going to have to confirm that that is the case. All right, so let's highlight our important info. Let's take the function itself, the domain, and we'll say odd function here. Okay, so to start us off, let's talk about, so an odd function is, as I said, is when if f of negative x is equal to negative fx, then that means we have an odd function. Okay. Equally, I'm going to write in as well what an even function would be, just because it's worth knowing. All right, and that is f of negative x is equal to f of x. All right, so it's a bit of bonus. Just an extra bit. So we don't need that. So to show that we have an odd function here, I'm going to have to show that f of negative x is equal to negative fx. Well, f of negative x is essentially we're just going to be lobbing in negative x for x in our function here. So we're going to get negative x times by the square root of 1 subtract negative x squared. And this has to equal negative f of x. So for this one, we're going to just put a negative sign at the start of the function and then sort of lob it into some brackets. And 1 minus x squared. Okay, so now looking at the left-hand side here, we've got negative x in brackets at the start, so we can just sort of take that out of the brackets. And then what you have to sort of identify is that negative x squared is just going to equal x squared, right? Because negative times negative is a positive, so that's just going to be x squared. So we get 1 minus x squared under our square root sign. And now we look at the right-hand side, we're going to get negative x, all right, and then just multiplied by, I'm going to be somewhat lazy and just take this, just multiplied by the square root of 1 minus x squared. And there we can see they are the same function, all right, so therefore we'll conclude that these equal, so f of x is an odd function. Cool. And there is the answer to part A. Okay, on to part B. And so we are told that the range of f is A is less than y, which is less than b. So the range of f is between A and B. A and B are elements of real numbers, and we're asked to find the value of A and B. So let's look at the graph that we have visually and kind of illustrate what we're going to be finding. Okay, so if we zoom in here and we go from this minimum point here, all right, that means this minimum point here, this is going to have to represent, this y value is going to have to represent A, because we're told that that was the minimum value of f. And also this maximum, this maximum value, let's go up here. This maximum value is going to have to be equal to B. All right. Now we're also told that the graph of f here lies between -1 and +1, so we can sort of note that this must be -1 over here. This must be +1 over here. I'll give it a little top and a hat. Okay, so the corresponding x values for this minimum here and the maximum here will have to be, the absolute value of that will have to be less than 1. Okay, and so how about we also note then that the corresponding x value for when y is equal to a, or when fx is equal to a. Let's say we can call this x underscore a, and same idea for the b one. Let's bring this down and let's call this x underscore b. All right, and so what you essentially need to identify here is that the gradient at the minimum, or at the turning point, so the minimum point and the maximum point, will be equal to 0. Both of their gradients, are equal to 0. And so if we take the first derivative of our function f and find when that's equal to 0, that will help us find the xa and xb, so the corresponding x values for the value of a and the value of b. We'll take them and plug that into our function f, and then that will give us our values of a and b. Equally, towards the end, I'll note as well, since we found in part A that this is an odd function, we won't need to plug in xa and xb into our function f. We'll just need to find, do one of them, and then we can use the fact that this is an odd function to find the corresponding value. All right, we'll get to that in a bit. All right, so let's copy down. Let's copy down our diagram. Let's copy this down. Let's take it in a slightly nicer picture. Let's copy that. We'll go to a new page. Let's bring that there, and we'll say part B. And so we're trying to find the values of A and B, and fx is equal to x multiplied by the square root of 1 minus x squared. So now, in order to differentiate our function f here, we're going to need the product rule and also the chain rule, okay? Since, the fx is the product of two separate functions, first function being just x itself, and the second function being the square root of 1 minus x squared. And then in order to differentiate that bit, square root of 1 minus x squared, we're going to have to use the chain rule. All right, so let's go over to our formula booklet and find these rules, which I've somewhat conveniently got here. Let's bring these over. That's the one. All right, so these are the rules that we're going to have to apply. Okay, so let's go through, and so let's just look at the product rule for now. So when y is equal to uv, the derivative of y is u multiplied by the derivative of, or dv dx plus v multiplied by the derivative of du dx. Okay, so sometimes this is looked at as, I know this is technically a little bit, I know the u dash idea is only really, or using dashes for derivatives is only really applicable for functions. So I like to sort of visualize it like that. So u dash v plus uv dash. And also one thing I wanted to note here is that the order in which you do these doesn't matter, since we are adding them together. So the order only really matters for the quotient rule. All right. So let's have a look at this and let's apply these rules. Okay. So if we have, so we'll say u is equal to just x, our function here, and we'll say v. So that v looks almost like a u, is the square root of 1 minus x squared. Now I'm going to rewrite this. So v is in surd form here. Now I'm going to rewrite this in exponent form, which makes it easier to differentiate. All right, so that is going to be 1 minus x squared to the power of a half. Okay, this is because the indices law, or I guess the indices law, is the square root of, let me clean that up a bit. In fact, we'll write it here. The square root of k is equal to k to the power of a half. All right, you're not familiar with your indice laws, I would recommend brushing up on it. You just sort of Google indice laws, you'll probably get a whole bunch that pop up. Yeah, which would be worth knowing. Okay, so first of all, let's find the derivative of u, which is relatively straightforward. The derivative of x itself, derived with respect to x, is just 1. Okay, so we'll put that there. And then now, if we want to find dv dx, now you can go, so essentially if you look at this, the rule or the formula that you're given in your formula booklet sometimes can lead to some confusion. What it's essentially saying is that if y is equal to g of u, where u is its own function of x, then dy dx is equal to dy du times by du dx. Now that works, and obviously it's obviously correct. The way I prefer to potentially look at it is you cover up what's within your bracket here and just differentiate around the bracket. Okay, basically as if the bracket's its own sort of term, or it's like it's an x term, right? So if I'm doing that, then this is going to be, well, bring the half to the front. Okay, then you put what's within the bracket just down here. So 1 minus x squared, untouched. All right, and then we, as per normal, subtract 1 from the subtract 1 from the power. So then we get negative a half. Okay, and then the next step is to then just multiply by the derivative within the bracket. Okay, so you derive the bracket as a whole and then multiply by the derivative within the bracket, right? And the derivative within this bracket is going to be negative 2x, okay? Because derivative of 1 minus x squared will be negative 2x. So we'll put times by minus 2x, right? Now we can clean this up a bit and put it back into surd form, which will help us later on. So let's put this, we're going to say this is equal to, well, something else. And yeah, I'll take a couple steps here. So it's going to be 1 over 2, actually, beg your pardon, let's call it just 1 over 2 multiplied by the square root of 1 minus x squared. So I've essentially done this rule in green over here in reverse. And then we're also going to have to then times by negative 2x. And we'll see that the 2 here and the 2 here can cancel out, right? And so then we can say we are left with, I'm just going to make this slightly smaller. Let's go there. We will be left with negative x over the square root of 1 minus x squared. And beg your pardon, that's not put a square there. 1 minus x squared. Let's clean that up a bit. 1 minus x squared. Okay, great. So now we have du dx, which is just equal to 1. We have dv dx, which is equal to negative x over the square root of 1 minus x squared. So therefore, the first derivative of x is equal to, so u dash v, or u times by dv dx, or whichever way around you want to do it. The order doesn't matter in here. So we're going to say x multiplied by dv dx, which is here. So I'm just going to sort of lob that into a big bracket. All right, and then I can add on v multiplied by du dx, which is just 1, so it's just going to be v. So we can just bring this over here, bring this down there. All right, cool. And then if we want to clean this up a little bit, we can say that let's say we've got negative x squared on the top over the square root of 1 minus x squared. Let's just copy this, bring that there, plus then the square root of 1 minus x squared. Okay, And then now we're going to have to find the x values that make this equal to 0, all right? And those x values will be xa and xb, as shown in our little diagram up here. Okay, so what we can do from here is we can say that let's bring our x squared to the, let's say here, let's add the equivalent of this. So hold on, let me just change this into, where's my blue colors gone? We'll go into this. All right, we'll add this to both sides. Okay, and then so essentially our right hand side is going to turn into, so therefore the square root of 1 minus x squared will equal x squared over 1 minus, or the square root of 1 minus x squared. Okay, and then now what we can do is we can multiply both sides by, we could say here, and let's bring this over so it's slightly more central. Okay, and now we can multiply both sides by the square root of 1 minus x squared. So let's say times by the square root of 1 minus x squared. I wonder if I can change the style to the colors that I like. No, it doesn't even matter. All right. Okay, and so then if we do that, times both sides by the square root of 1 minus x squared, we're going to get, the square root of 1 minus x squared times by the square root of 1 minus x squared will just be 1 minus x squared. All right, so we'll get that on the left-hand side here, 1 minus x squared. And then that's essentially going to cancel out the denominator on our right-hand side, so this is going to be equal to x squared. All right, then now if we add x squared to both sides, okay, we're going to get just 1 by itself on the left-hand side, and then we're going to get 2 lots of x squared on the right-hand side. Okay, and then we can sort of say, therefore, then, we can divide by 2 from both sides. Let's do that. We'll say divide 2 but from both sides, and we can, we're going to say we get a half is equal to x squared. Okay, and then we'll take the square root of both sides. All right, and then that's going to give us, so this is where a lot of errors sort of come in. So the square root of a half is equal to plus and minus the, plus and minus the square root of a half. Squared will be a half. Right, so we get the answer being plus and minus the square root of a half, which is the same as just saying 1 over the square root of 2. And then this is equal to x. And we need a new page, so let's bring this down. All right, so that means therefore x a is equal to negative 1 over the square root of 2, and x b is equal to 1 over the square root of 2. Check this. All right, now let's say if we lob in either one of these into our function f. So let's lob in a is equal to f of xa, which is going to be equal to, so fx was negative 1 over the square root of 2 multiplied by the square root of 1 minus x squared, so which is going to be negative 1 over the square root of 2 squared. All right, now if we go through and work this out, we're going to get negative a half, negative well, that's going to be negative 1 over the square root of 2 multiplied by 1 minus, so this is just going to be a half. Let's bring this there, and so this is equal to negative 1 over the square root of 2 multiplied by the square root of essentially a half, which we know is 1 over the square root of 2. And this just equals negative a half. All right, so then therefore, a is equal to negative a half, beg your pardon. And now, since we know that f is an odd function, so of course, what you could do also here is lob in xb into our function f, and that will give us the value of b, which would be absolutely fine. Though what we can also, we could sort of skip a bit of a step here and go back to sort of the idea that in part A, we found that f of x is an odd function, right? And so we could sort of say, since f of is an odd function, then f of negative 1 over the square root of 2 will equal negative of 1 over the square root of 2. All right. Now, we already found that this here was equal to a. So that one was equal to a. Now, this is essentially saying this here, this would be what we would use to find the value of b. And this is essentially saying that a is equal to the value, of negative b. And so then we can conclude that therefore b is equal to a half. Okay, and then that is the answer to part B. Right, question 7. By using the substitution u equals sec x or otherwise, find an expression for the definite integral between pi over 3 and 0 of sec to the power of nx multiplied by tan x dx in terms of n, where n is a non-zero real number. Right, okay, let's charge on. So let's highlight this idea of using this u substitution. Okay, and we're going to have to rewrite our definite integral here in terms of u, and then integrate it with respect to u as well. All right, so let's go over to our formula booklet and let's get a bit of info that we're going to need. So we're going to need the, I'm going down here, the definite, the derivative of sec x. So we've got that here. Let's bring this over. This is going to be helpful. And we're also going to need to know the idea of what sec x is, and it's 1 over cos x, which is also in your formula booklet. If we go up to here, where are we? Did I go past? No. Section 3, right? Yeah, here we go. So reciprocal trigonometric identities. So this one here. Okay, so let's bring this over. All right, yeah, that'll do. Let's maybe make that bigger. Okay, so first things first, we're going to need to make our u substitution. Okay, but then we're going to need to integrate our integral with respect to u. So we're going to need to have du on the end. Okay, so if we go through and sort of find, well, if u is equal to sec x here, that means therefore du dx is going to equal what we have, just over here. All right, so that's sec x tan x. All right, so the best thing we can do, or the ideal situation, is we can get an expression for du that looks something like this, tan x dx. And then we can sort of just replace tan x dx with du, or the little manipulation that we may do to du, and then we can sort of have a integral with respect to u. Okay, so if we rearrange this this thing here, we could say we've got du is over sec x. All right, so dividing both sides by sec x and by and multiplying by dx. In fact, we'll show that. This is going to equal tan x dx. All right, which is identical to the end. We go here to the end of our integral in terms of x. All right, now let's say what we've done here. So here, going down, what we've done is we've multiplied by dx. How much we can say multiplied by dx over sec x. That's effectively what we've done here to rearrange it to this. And I'm also going to actually make another adaptation here. And what we can recognize is that du over sec x would just be the same as du over u. Or alternatively, what we could say, we could say that du over u. Or alternatively, you could call it 1 over u multiplied by du, which is effectively what we're going to end up using for our definite integral. Okay, so now we have an expression for du, which is then divided by u, and that equals tan x dx. So we can substitute in, we can sort of swap in this du over u for tan x dx, and then make our u substitution, right? That's going to look a little bit like this. All right, so let's go for it. We're going to go, oh, not got my pen. All right, so it's going to be u to the power of n divided by u and then du. All right, we're going to have to say that in this here, we've got x is equal to pi over 3 up the top here, and then x is equal to 0, because we're also going to have to make we're going to have to change our x values to be in terms of u, right? And that's what we're going to do in the next step. Let's just bring that down to there. All right, cool. And also I've brought this u to go under the un, all right? If it was under the du, you bring it over, okay? Same thing. Okay, so now we're going to think, if x is equal to pi over 3, then what would u equal, okay? So if we come over here and we have a look, we can say we've got x is equal to pi over 3. Therefore, u is equal to sec pi over 3. All right, which is just going to equal the reciprocal of cos pi over 3. Right, so 1 over cos pi over 3. And if you remember your exact value triangles, or here's the right-angled exact value triangle for pi over 6 radians and pi over 3 radians. It's essentially an equilateral triangle with side length of 2, and then you cut it in half, as you can kind of see there, and then that gives us all our values for pi over 6 radians, pi over 3 radians, and so on. Okay, so that means if we have sec pi over 3, and we know that cos pi over 3 is going to be adjacent over hypotenuse, which is a half. So it's effectively going to be the inverse, or sorry, the reciprocal of a half, which is going to be 2, okay? Because cos pi over 3 would be a half, so then sec pi over 3 would be 2. And now if we do the next step for here, we can go x is equal to 0. That means u is equal to sec of 0. And the best way to answer this would be to just sort of go back to your the cos graph, right? We know at 0, it's at 1, right? So that means that equals 1, right? A nice, easy way you can do that. And I recommend sort of being able to do a quick sketch of your graph. That's definitely far from perfect, but it doesn't need to be perfect. So that's the cos graph there. And the sine graph, starts at 0 and goes like that, okay? A little way you can remember that is that C comes before S in the alphabet. So the cos graph starts at 1 and the sine graph starts at 0. That's a little way I've gone to remember it, but yeah, you can just memorize it, I suppose. Yeah, there we go. Let's get rid of the sine graph because we don't really need that. Okay, sweet. So then now moving on, we can sort of make our full u substitution and substitute them in for the x values. So that's going to look a little bit like this. What I could even do is just copy this down and we'll get rid of these. And we'll say that the u values are from 2 to 1. And equally what we could do, we can change this expression un over u. We can change it to u to the power of n minus 1. All right, because this rule is from the indice law. That is, if you have, let's say, a to the power of m over a to the power of n, this is equal to a to the power of m minus n. All right, so little indice law there to memorize, okay, and it'll help us out. All right, so now we're just going to run through and use our normal integration rules with respect to integrating with respect to u. And so that's going to look a little bit like this. We're going to get, well, adding 1 to un minus 1 will be just n. All right, and then we're going to have to divide by the new power that we have, which is n minus 1 plus 1, which is just going to be n. And now we're integrating this between the limits of 2 and 1. And so then this is going to equal 2 to the power of n over n, subtract 1 to the power of n over n. Now, 1 to the power of anything is just 1, all right? So that's just going to be, oh, whoops, sorry. Line those up a bit better. All right, so 1 to the power of anything is going to be 1. So we can just replace that, and we have a common denominator. So then our final answer is going to be 2 to the power of n, subtract 1, all over n. And that is the answer to question 7. Okay, question 8. A continuous random variable x has the probability density function as follows here, okay? The following diagram shows the graph of y equals fx for x is between a and b. Right, given that c is greater than a plus b over 2, find an expression for the median x in terms of a, b, and c. Right, cool. So let's talk about a little bit. Let's show what's going on here. So we have this PDF up here, which we're going to obviously need to use, and we're, quite kindly we're told this idea here that c is essentially greater than the average of a plus b of a and b. We can also just see that from our graph here. If we just draw, let's go with purple. We just draw this line down here. This is essentially where this point, or the apex of the triangle. That is where that's not very good, is it? That's where the function changes. So that means that's going to have to be c there. Okay. Now, in order to find an expression for the median, we're going to have to essentially split this triangle in half. Okay. So let's say if we call let's call the top of our triangle up here, let's just call this we'll call it point D. All right. Triangle ABD, the area will have to equal 1. All right. Now, if we introduce, put the median down here. All right. And then let's say we find a point here. All right. E, let's just call that E. That means triangle AME will have to equal a half. Okay. Because half of the values lie to the right of the median and half the values lie to the left of the median. Okay. And so from that, we can now go ahead and sort of calculate or sort of use the fact that the median or the triangle AME is equal, the area of that triangle is equal to a half. We can use that to then now find an expression for the median n. So with this triangle here, AME, the base will be just m minus a, which is just this line here. All right, so that's just going to be equal to m minus a, and the height is going to be when we substitute m into our probability density function. Now, since we know that m is to the left of our of c, that means we're going to have to lob m into this probability density function. Right, bear with me here. I'm going to try and make that slightly better. In fact, we'll just do two lines, right? That's probably going to be better. I will just put a box around it. That's probably even better still. So we're going to need to use this part here, this probability density function, or the first part of our probability density function, because M lies within A to C. All right, cool. So that means then the height of our triangle will be equal to, and we substitute M into this guy here. And so what I'm going to do actually is just copy this down so I don't have to keep on going up and down. Let's just paste that there. So the height is going to be 2 over B minus A, C minus A, and then multiplied by M minus A, because we're substituting in M for X. All right, so now we have the base of our triangle, we have the height of our triangle, and we know the formula for the area of a triangle is equal to half base times height. All right, so we can say, therefore, the area of, say, triangle AME is equal to, well, we know it's equal to a half, which is equal to 1/2 times by, or in fact, we'll just put times by the base, which is over here, M minus A, multiplied by the height, which is here, which I am going to just, we'll put in some square brackets and copy it down. Cool. And actually, hold on, let's make it slightly smaller. Nice. Okay. So now we have, an expression for the area of the triangle AME, which has M in it, and we can go ahead and sort of solve this now. So what we can do is say a half is equal to, we could say that this half here will cancel with this 2 up here. All right. Equally, you could have divided both sides by a half, and then gone 1 on the left hand side. Any way you want, you can sort of rearrange this equation to find M. All right. So we're going to end up having M minus A multiplied by M minus A on the numerator. So we'll just get M minus A squared. Let's move this slightly over, and then we're going to get on the denominator B minus A multiplied by C minus A. C minus A. All right, lovely. And then so now what we can do is, let's rearrange this. And so let's multiply both sides by B minus A multiplied by C minus A. And so let's just take this down and we'll say what we're doing. We're going multiplying by B minus A multiplied by C minus A. Okay, and so that's going to get rid of this denominator here. So we're just going to get B minus A. In fact, I'm going to kind of copy it. Let's just bring this down here. B minus A over C minus A, and then that's going to be over 2 is equal to M minus A squared over 2 equal to M minus A squared. As per usual, I'm probably going to run out of room, so I'm just going to add a new page on the bottom here. Okay, cool. And then what we can do here is we can square root both sides. So yeah, we'll put one more step into here. So square root both sides, and so we'll get the square root of B minus A over C minus A, B minus A multiplied by C minus A over 2. Square root of that is going to equal just M minus A is equal to M minus A. And then now we'll add, in fact, we'll just copy the exact same step down to our new page, okay? Bring that down here. And then now next step, we're going to add A on both sides. All right, and actually what I'm going to do is I've need to lob in, if we're taking the square root of anything, we're going to have to remember to lob in our plus and minus sign, okay? We end up only needing the positive version of this since m is greater than 0. So yeah, well m is greater than a, so we need it to be the positive version, but for it's good practice to always lob that in. I'll show you why that turns out. So here we're going to add an a, so plus a, and so we'll get, and that's, yeah, we'll go, and we'll say m is equal to this plus and minus square root of b minus a times c minus a over 2 plus a. All right, and then, yeah, as I said, since we know, since we'll write since m is greater than a, we don't need this this negative version, because that would make it make this expression less than a. All right, so since m is greater than a, therefore m is equal to, let's go with a plus the square root of this. Let's go here. And now that is the answer to question 8. Question 9. Prove by contradiction that the equation 2x cubed plus 6x plus 1 equals 0 has no integer roots. Okay, so when we prove something by contradiction, what we essentially need to do is assume the opposite to be true, all right? And then show at the end that there is a contradiction to our assumption, and therefore, you know, there are no integer roots in this circumstance. Okay, so the most efficient, there's a number of ways we can go around proving this statement by contradiction. I suppose the most efficient way would be as follows. All right, if we let fx equal our function here, so 2x cubed plus 6x plus 1, and we'll say that f of a, or alpha if you prefer, f of a is equal to 0 for a is an element of integers. All right, so if we do that, now what we can do is, if we take the first derivative of our function f and find f dash x, and we see this is 6x squared plus 6. Now we can notice that this equation here will be greater than 0 for any value of x, or for x is an element of any real number. Okay, so for x element of real numbers. So basically by that, what it means is, if we had a graph, all right, our function of f always has a positive gradient. It's not a straight line, it'll have some curvature to it or something like that, but it will always be positive. We'll always have a positive gradient. Equally, we can see that the lowest gradient for f, for our graph of f, will be, meant to be a highlighter, will be 6. Okay, and then no matter what x value we put into here, well, if x is equal to 0, then the gradient of the graph of f is going to be 6. It's going to be 6 times 0 squared, which would be 0 plus 6. And then, you know, if we put a -1, it's going to be 6 times -1 squared, which is 6 plus 6. So the gradient there will be 12. All right, 6 plus 6. Equally, if it was 1, you know, when x is equal to 1, 6 times 1 squared will give us 6 plus 6, and so 12. All right, so basically the point I'm trying to make is that no matter what x value we put into our first derivative, it'll always be greater than 0, always greater than 6 even. And that means that the gradient of the graph of f is always positive. All right, or another way we can say is, therefore f is a strictly increasing function Okay, so now that we know that the graph of f is always got a positive gradient, so it's never has a negative one, never comes down. Let's go ahead and try and find roughly the range in which, a range in which the graph of f crosses the x-axis. All right, so when y is equal to 0, or when fx does equal 0. All right. Now, if we go and have a look at when when x is equal to 0, and we lob this into our function, we'll get 2 lots of 0 cubed plus 6 lots of 0 plus 1, and we see that this is 1. All right, so therefore we have the coordinates on the graph of f of 0, 1. All right, and now if we put in x is equal to -1, we're going to get 2 lots of -1 cubed plus 6 lots of -1 plus 1, and we'll find that this is equal to -7. All right, and so therefore there are the coordinates on the graph of f of -1, -7. So that means somewhere between x is equal to 0 and -1, the graph of f will cross the x-axis, all right, which will be the root, right? But given it's between 0 and -1, that means the root can't be an integer number, because that would have to be, an integer has to be a whole number, okay? So we can then sort of conclude that fx equals 0 has one real root, or let's say x is between -1 and 0, and then hence this is sort of contradicting our initial statement, and so we'll conclude that 2x cubed plus 6x plus 1 equals 0 has no integer root. The way we're going to say that is we'll say contradicting our assumption that f of a equals 0 for a is an element of integers. So, and we can conclude hence 2x cubed plus 6x plus 1 equals 0 has no integer roots. Cool. And that is the answer to question 9, perhaps the most efficient answer. Another possible solution or way to go about this is to consider different integer values for a. Okay, so basically when a is a positive integer, when a is a negative integer, and when a is equal to 0, and you'll find when you sort of plug them into our equation here that none of them will give a value of 0, and that's equally a perfectly fine sort of proof by contradiction that this equation has no integer roots. Yeah, there we go. That's the answer to question 9. Okay, question 10 for the HL exam is here. There we go. This one here. All right, which is is identical to question 9 from the SL exam, which is here. Okay, everything being the same, all the marks are the same, and all the values are the same. So the following recording is my work solution to question 9 from the SL exam. Okay, question 9. So the way we are going to look at this question is it's effectively actually 2 questions. You've got parts A, B, and C, which are all relating to this first probability distribution. And then you've got parts D and E, which almost feel like a completely new question. So we will, first of all, let's just look at parts A, B, and C together, and we'll answer them, and then we'll go on to that next bit. All right. So a biased four-sided die with faces labeled 1, 2, 3, and 4 is rolled and the result recorded. Let X be the result obtained when the die is rolled. The probability distribution for X is given in the following table, where P and Q are constants. Okay, so first things first, that we are gonna end up having to use this fact, but the probabilities of all these numbers here, including the constants, they're going to have to add up to 1. Okay, so that's always the case when you sort of roll a die or flip a coin. The probability of each event occurring, the sum of each of the probability of each event occurring, they need to add up to 1. So, for example, flipping a coin, 50-50 for heads and tails, given it is an unbiased coin. So moving on, we have for this probability distribution, it is known that the expectation of X, so EX is equal to 2. Part A asks, show that P is equal to 0.4 and Q is equal to 0.2. And then find, let's just look at part A for now. And what we will do is we'll take all this, we'll bring this down to a new page. Bit more room. Okay, cool. Lovely. So given that we know that each event, the sum of the probabilities of each event, we know that these are going to have to add up to 1. So that can be our first equation, right? So we're going to write that in. So we're going to say P plus 0.3 plus Q plus 0.1. This is going to have to equal 1. All right. And then now if we wanted to sort of simplify this or clean it up a bit, we could sort of bring the 0.3 and the 0.1 to the other side. All right, so we can subtract that. So the sum of them would be 0.4. So if we did that, come down to a new line and say subtract 0.4 from each side, that would give us P plus Q is equal to 1 subtract 0.4, which is 0.6. All right, cool. So there is a start. Okay, so there is an equation in terms of P and Q. And funny enough, we can see that if P was 0.4 and Q was 0.2, that would satisfy this equation. But now to completely show that, to confirm this, we're going to have to use this information here that the expectation of X, so the expected value of X, is 2. Now the formula for the expected value of a probability or of a probability distribution is given to you in your formula booklet. Let's just go have a look. And so that is going the wrong way, sorry. Down here we have expected value of a discrete random variable. All right, so here, in fact, we'll include the little SL bit so you can see whereabouts in your formula booklet it is. Okay, and so this bit states here, let's lob that up there, that EX is equal to X, little x, which is this line up here, that line up there, multiplied by the probability of that given X value occurring. Okay, and it's the sum of that. That's what this sigma sign equals. Okay, so that means EX, which we are told is equal to 2, will have to equal 1. So that's taking up the 1 bit there, multiplied by P, okay, because that's the probability of X being equal to 1. All right, then moving on, so then we're going to have to add up the next one. So this is going to be 2 multiplied by 0.3. All right, then plus 3 multiplied by Q plus 4 multiplied by 0.1. Okay, and so then that's going to have to equal 2. So now if we go through again and we sort of clean this up a bit, we're going to get 2 is equal to, well, 1 times P is just going to be P. 2 times 0.3 is going to be 0.6. Okay, 3 times Q is going to be 3Q. Okay, and 4 times 0.1 is going to be 0.4. So we'll put that over here. And then now to clean it up again and sort of have an expression in terms of P and Q just by itself, what we will do is we'll subtract the sum of 0.6 and 0.4, which come to 1. So we'll just subtract 1 from both sides. That will leave us, I'm going to swap the sides here so we can sort of get our P and Q on the left-hand side, sort of in a similar fashion as we have up here. So we're going to get P plus 3Q is equal to 2 subtract 1, which is just 1, right? And so now effectively you have two equations. We can call this equation 1 and this equation 2. All right, and now we're going to have to run simultaneous equations or sort of solve these equations simultaneously. There are a few ways you can go about this. There is the elimination method, which I'm going to use here. There's also the substitution method where we could sort of get an expression. Yeah, definitely I'd say recommend probably using this one here. We could say that Q is equal to, or even P is equal to 0.6 minus Q. And then we can substitute that in for our second equation. That's a valid method, but I'm going to show you the elimination method in this case, because we have we've got sort of just 1p here and 1p here. All right, so what we're going to do is effectively the equation 2 subtract equation 1, and that's going to look a little bit like this. Okay, so we're going to sort of write equation 2 on top, and so we'll write P plus 3Q is equal to 1, and now this is going to be subtract P plus Q is equal to 0.6. Now I draw a line under this, and now we sort of subtract all the terms, and you'll sort of get from the name that I said the elimination method. And so essentially what happens here, because the coefficient of our p's are the same and we're subtracting the two equations, the p's are eliminated from the equation. So we get p minus p, which is nothing, and we get 3q subtract q, which is going to give us 2q, and then this is equal to 1 subtract 0.6, which is equal to 0.4. Okay, and then we can sort of then say, therefore, if we divide both sides by 2, we'll say divide by 2, and we can say that means Q is equal to 0.2. And then now what we're going to do to find the value of P, or show that the value of P is, as we're sort of told here, 0.4, I'm going to substitute in, okay, sub Q is equal to 0.2 into either equation, but in an exam, I would say venture to suggest or encourage you to use the easiest and most efficient equation possible. And in this circumstance, it would be equation 1. There's less calculations to do. All right, so we're going to sub that into equation 1, and so that's going to be P plus 0.2 is equal to 0.6, and then we'll do a little sign. We'll subtract 0.2 from both sides, which will get our P by itself, and we get P is equal to 0.4. And then that is the answer to part A. Okay, on to part B. So part B asks, find the probability that X is more than 2. So we'll go through and do similar process as before. Bring this down to a new, we'll go onto a new page. All right. And so we already know that P is equal to 0.4 and Q is equal to 0.2. And if we're finding the probability that X is greater than 2, and we have here a discrete random variable, that means the two possibilities that we need to consider is the probability that x is equal to 3, all right, plus the probability that x is equal to 4. All right, cool. And we can quite easily get that from the q, which was 0.2. We could even put 0.2 here. We can put 0.4 over the top there. And so this is going to be 0.2 plus the probability that x is equal to 4, which is 0.1. And so the answer is 0.3. And I'm going to copy this down for each line. And there we go. That is the answer to part B. Okay, on to part C. Let's go up. So Nikki plays a game with this 4-sided die. In this game, she's allowed a maximum of 5 rolls. Right, let's highlight that up. Maximum of 5 rolls. And we'll extend it to include the idea of it being the maximum. Okay, her score is calculated by adding the results of each roll. Nikki wins the game if her score is at least 10. Okay. After 3 rolls of the die, Nikki has a score of 4. Okay. Part C says, assuming that rolls of the die are independent, right? So that's going to be important, the fact that they are independent. Find the probability that Nikki wins the game. All right, and then after 3 rolls, her score is only 4. She has a score of 4, which is somewhat unfortunate when we think about, how she's managed to get a score of 4 and from 3 rolls. And if we look back at our, our table up here, okay, you see the only way she will have managed that is by getting 2 1s and then a 2. So she started off pretty unlucky in this game, to say the least. All right, let's copy down information to a new page, and we'll go from there. All right. Yeah, we can go. We'll put it in here. All right. So if she's already done 3 rolls, okay, that means she must have 2 left. Yeah. So we'll put in C here. And we'll say Nikki has 2 rolls left, and in order to win, she must score 10. She must score 10 from the 5 rolls. So, and if she's already got a score of 4, that means she must score at least 6 in these 2 rolls. Okay, so she has 2 rolls left and must score at least 6 to win. All right. Okay, so now we've got to consider the possibilities of Nikki scoring 6. Okay, so if we look back at our table, in fact, what we could do, we'll just copy this bit here and bring that off to the right. Let's do that. Paste image. Yeah, that'll do. That's not too bad. Okay, cool. So the ways that she can score a 6. Okay, so the probability, so we'll say P win. So the probability that Nikki wins will be the probability that she rolls a, well, we can't make any sum of 2 rolls with using 1. So if she gets one more 1, right, considering she's already got 2, because if she's on 3 rolls and gotten a score of 4, that means she will have had to roll 2 1s and 1 2, which is unfortunate. Yeah, so she can't roll a 1 at all. She could roll a 2 on the first roll, all right, and then a 4 on the second roll. She could do that in reverse order as well. So she could do a probability of a 4 and then a 2. All right, then the probability of getting a 3 and a 3. All right, there we go. And then equally, we could say if she got the probability of getting a 4 and a 3 and a 3 and a 4, because that would add up to 7, which is at least 6. So that's also going to count. So we'll say plus probability of a 4 and a 3 plus the probability of a 3 and a 4. And then equally, if she rolled 2 4s, that would sum up to 8. And so that would also be okay. That would cause or make Nikki win. So probability of a 4 and a 4. Okay. And so now if we go to our formula booklet and we try to find the probability of 2 independent events occurring, we will see that in our formula booklet here. Let's go find it. It's in the 4 section, topic 4. And so here, all right, so this idea here, independent events, okay? The probability of A and B occurring, okay, is the probability of A times the probability of B. All right, so that's what we're going to need here. Let's just take that, copy that over. What am I doing? Sorry, we'll lob that there. All right, so then now in order to calculate the probability that Nikki wins, we need to add up all these probabilities. And in order to do that, we're going to need to multiply. So for the first one, we're going to have to multiply the probability of getting a 2 and then a 4. Okay, so we're going to have to find the product of that. So that's going to be 0.3 times by 0.1. Okay, and then we get the same thing, but in reverse order, which is going to equal the exact same thing. So I'm going to write it all out. But what would be also, equally fine and probably more efficient in an exam is you could just multiply this bit here by 2, just one of them by 2. And if you put a coefficient of 2 and you're working, the marker will know what you're doing and they'll see that you understand that they're going to be the same thing. But I'm going to write out each thing as their own occurrence, if that makes sense. All right, so then the next one is going to be probability of a 3 and then a 3, which is going to be 0.2 times by 0.2. Equally, you could just put that as 0.2 squared. Probability of a 4 and a 3 is 0.1. 0.1 times by 0.2 plus the probability of then a 3 and a 4, which is 0.2 and 0.1. Sorry, yeah, the exact opposite of that. So that switched around. And 2 4s is 0.1 times 0.1 or 0.1 squared. Okay, and so now we're going to have to go through, calculate all of this. So 0.3 times 0.1 is going to be 0.03. Okay, 0.1 times 0.4 will be 0.04. Sorry, 0.2 squared or 0.2 times 0.2 will be 0.04 as well. 0.1 times 0.2 will be 0.02. And yeah, that's repeated for the next one as well. 0.2 times 0.1, so 0.02. And then 0.1 times 0.1 is 0.01. Okay, cool. Now we're just going to add all these up. So we got 0.03 plus 0.04 plus 0.04 plus 0.02 plus 0.02 plus 0.01. And that will give me the 0.15. Okay, take your time with these ones. It's quite easy to get them off by sort of one digit. But yeah, I recommend just going through. So 0.03, 0.04, so you get to 0.07, then 0.11, then 0.13, 0.14, then 0.15 at the end. You kind of saw how I went through there like that as we work from left to right. Okay, and then that is the answer to part C. So that's the probability that Nikki would win the game. Okay, now let's move on to part D. Okay, so part D and E, brought them down to a new page. So David has 2 pairs of unbiased 4-sided dice, a yellow pair and a red pair. Both yellow dice have faces labeled 1, 2, 3, and 4. Let S represent the sum obtained by rolling the 2 yellow dice. Probability distribution for S is shown below. Okay, cool. So that's given here. First red die has faces labeled 1, 2, 2, and 3. And the second red die has faces labeled 1, A, and B, where A is less than B, and A and B are both an element of positive integers. Okay, the probability distribution for the sum obtained by rolling the red pair is the same as the distribution for the sum obtained by rolling the yellow pair. Okay, cool. And part D asks, determine the value of B. So when we think about our two dice, our two red dice, red dice, we'll say on our first one, okay, we have 1, 2, 2, and 3. And then let's put our second one here, where we've got 1, A, and B. Okay. And we know that A is less than B. Okay. And when we look at the probability distribution that we've got up here, okay, if we look towards the 8 column, all right, there has to be only one possibility from rolling our two red dice, that sum to 8. Okay. And then when we look at our the possibilities that we have, we can get sort of 1 and 1, all right, and that would represent 2, and that will give us our 1/16. So that's already taken care of. We're going to get 1 and A, 1 and A again, and 1 and B. All right, so we're not going to be too concerned about the 1 idea, because there's no way we're going to be able to get 8 or just one value of 8, and that being our highest value. So we've got to skip all the way to the 3 on the first dice. Okay, so we're going to assume that we have rolled a 3, and then there has to be one possibility from rolling the second dice where the sum of our two dice will add up to 8. I hope that made sense. Okay, so if we went for 3 and a 1, we would get 4, and so that's not going to be good. We could get 3A and then 3A again, and if that was to sum to 8, so let's say if A was 5, okay, that means we'd have to have two possibilities of summing to 8, and then we'd also have to have a possibility that is a sum that is higher than 8, because we are told that A is greater than B. So other way around, so A is less than B. So with that being said, why is that constantly giving me a little dot? So yeah, there we go. All right, so with that being said, that means 3 and B will have to sum to 8, and there's only one possibility of that happening, which is 3 and B. So then therefore we can conclude that B is equal to 5. So yeah, a bit of thinking involved with that one. But yeah, so that is the answer to part D. Okay, and part E asks, find the value of A, providing evidence for your answer. All right, so the best way to go about this will be to create a table of sums or of results, from rolling the two dice. All right, so the way I'm going to go about that is I'll put the first dice up the top, so we can have sort of, we'll go 1. In fact, what I can do is I can even just copy this, right? I can just bring this down. 1, 2, 2, and 3, and then on the the vertical, in the columns, I suppose, we'll put the second dice. So we'll go 1, A, and B, and now let's. In fact, we know what B is. B is 5, so let's lob that in. 5. All right, and so now if we create this table, we'll go like this. There. Okay, cool. And now let's add in our vertical lines. All right. And let's just copy that. I'll just bring that over there. All right, sweet. That will do. And we'll bring these down. Okay, so now when we look at our first column, we've got a whole bunch of different possibilities, and let's put in right in the sum of each possibility. I'm going to put this in a new color. All right, so we're going to say, this is 2, because we get 1 and 1. When we get 1 and 2, which will be 3, 3, 1 and 2 will sum to 3, 1 and 3 will sum to 4. Okay, cool. Now on to the next line. So here we have a and 1, so we can call this a plus 1. Then this can be a plus 2, a plus 2, and then a plus 3. Equally, then this line is going to be exactly the same. A plus 2, and then a plus 3. And then lastly, we can put in 6, 7, 7, and 8. And so we have 16 possibilities in our table, which is correct from our probability distribution table, which I'm also going to let's bring that down as well. Okay, so let's stop that there. Now let's start to equate. So have we got one possibility, 1 out of 16, that is equal to 2, and that's correct. We've got that. We've got 2 possibilities that are equal to 3, which are here. Okay, 4 possibilities. Sorry. So the sum of 4, we're meant to have 3 possibilities. Okay, and we have 1 of them in our table, so that's going to be helpful. Or what have I done? We've got 1 of them in our table. Okay, and then so on and so forth. But the easiest way to answer this is that in our definite sum, so in this top line here, okay, and then this bottom line here, we have no options or no sums of 5. Okay, so that means therefore some of these sums here are going to have to add up to 5, right? And there's going to have to be 4 possibilities for them, all right? So if we get rid of these highlight here and we see which occurrence with A in it has 4 possibilities, well, that's going to be these middle 4 possibilities, okay? So these guys are going to be our 4 possibilities that add up to 5, all right? So I'm trying to, let's actually highlight all the individual terms as well, all right? So these terms here have to add up to 5, so if the probability that s is equal to 5 is equal to 4 over 16, therefore a plus 2 will have to equal 5, because that's the only one we have with 4 possibilities. And so then we can say, therefore, a is equal to 3. And that is the answer to part E. Right. Question 11. A function f is defined by fx is equal to 1 over x squared minus 2x minus 3, where x is an element of real numbers and x cannot equal -1 or 3. Part A asks, sketch the curve of y equals fx, clearly indicating any asymptotes with their equations. State the coordinate of any local maximum or minimum points and any points of intersection with the coordinate axes. Okay, cool. Now let's copy this down to a new page. Or chop a little bit of the one off there. And now let's have a look at what we've got. So first things first, we'll start with the idea of the asymptotes. And once again, it's relatively kind that we're given the values of x, which that can't, with values of x that are not applicable to fx, or we cannot substitute these x values into fx, because essentially what they will do is make our denominator equal to 0, and we can't divide by 0. And I said before in an earlier question that these essentially just give you the equation of the vertical asymptotes, right? So in fact, let's highlight our information. So we got asymptotes with their equations. We got coordinates of any local maximum or minimum points, and points of intersection with the coordinate axes. All right, so we'll go through these 3 things first, and then we'll get to sketching the graph of y equals fx. Okay, so let's first of all, we can put in vertical, and we'll put in a little a here. Okay. Vertical asymptotes are going to be x is equal to -1 and x is equal to 3. All right, so that's a nice one there. Moving on to the horizontal asymptote. Now this is the limit as x tends to positive and negative infinity of fx. And a bit of a hard and fast rule that you can remember is that if the degree of the denominator of a rational function is greater than the degree of the numerator, which is just 1 here, then the limit as x tends to positive and negative infinity will be equal to 0. And hence then the horizontal asymptote will be y is equal to 0, or just the x-axis. Okay, it's a bit of a hard and fast rule you can remember there. So therefore, the horizontal asymptote is y is equal to 0. Okay, that's nice. Now, so maximum or minimum points, let's go on to that. So the easiest way to calculate this, in my opinion anyway, is to use the reciprocal function of f, or just identify that fx is the reciprocal function of x squared minus 2x minus 3. Okay, so if we just said, let's use g, let's say gx is equal to x squared minus 2x minus 3. Okay, and what we could do is we could factorize this here, and we could say that this is equal to x plus 1 multiplied by x minus 3. Right, and we can see here that if we lob in x is equal to -1 into here, that will make the equation equal to 0. And equally, if we put in x is equal to 3 into this equation here, it'll make it equal to 0, which will mean then the graph of f will be 1 divided by 0, which we can't do, so that's why it's a vertical asymptote. Yeah, we've talked about that. So then the graph of g will have a minimum point, since it's a positive quadratic. Okay, so g min, or the minimum point of gx, will be the x value that is directly in between -1 and 3. Okay, and that's x is equal to 1. All right, and so now if we lob that into our function, and we'll get rid of the underline there, we're going to get 1 plus 1 multiplied by 1 minus 3, and that's going to equal 2 multiplied by -2, which equals 4. Okay, so then that means -4. It's equal to -4, which means then therefore the minimum g min is at 1, -4. Right. Now, a relationship between reciprocal functions that you can use here is that the graph of f, since the graph of g has a minimum point, that means the graph of f will have a maximum point because they're reciprocal functions, and the x value will be the same for both these 2 points. So for the minimum for the graph of g and the maximum for the graph of f. So we can say, we can go through and say, therefore, f max will be when x is equal to 1, and then the y-coordinate will just be the reciprocal of the y-coordinate in for g. Okay, so you can sort of visualize that, because if we put x is equal to 1 into f of x, we'll see that we get 1 over essentially -4, because we know what happens when we put it into that. We found that there. And so the answer here for the y-coordinate for the maximum point of f will be -1/4. All right, and so then now we have the maximum point and we've got our asymptotes. Now let's look at the intercepts with the coordinate axes. Okay, so the x-intercept, so the y-intercept, will always be when x is equal to 0. So we can say, let's put that y-int. In fact, I'm going to put this into blue. Let's say y-intercept is when x is equal to 0. So y-intercept is going to be f of 0, which we will see is 1 over, let's do the whole thing, 0 squared minus 2 lots of 0 minus 3. And we can see that this is just going to come out to be negative 1/3. All right, so therefore the y-intercept is 0, negative 1/3. All right, and then now the x-intercept. Intercept is when fx is equal to 0. And we'll see from our function here, so if we lob in, so f of x is equal to 1 over x squared minus 2x minus 3. Now, there are no x values that will make this equal to 0. So this can't equal 0. So therefore, no x-intercepts. So there aren't any x-intercepts. Equally, you could have got that from the idea that the horizontal asymptote is y equals 0, which is the x-axis. It's the x-axis, and that would have been equally a fine justification. Okay, so now we've got all the bits and pieces that we need. We've got the the intercepts, or the intercept, I should say, the y-intercept, the maximum point, and the asymptotes. Let's actually, why don't we just go through and we'll highlight what we need here. So we've got that guy, got this one, got the maximum point there, and we have the y-intercept. Okay, so now if we go down to, let's create a set of coordinate axes, and we'll graph our function. We'll have a sketch of our function. Okay, so first things first, let's put in the vertical asymptote. So let's put that in there. Let's say that's the one for x is equal to -1. Let's do a dotted line for this. So we'll go there, and actually let's bring this whole thing down slightly. Okay, and we'll label this y, x. Okay, and that is x is equal to -1. And also we're going to need to put in when x is equal to 3. Let's try and get this roughly right. Yeah, let's say there. And we're going to need our graph to go a bit further. No, don't want that. We just want this to come shoot off a bit there. Okay, cool. And then that's when x is equal to 3, this line here. All right, nice. And we don't need to draw the horizontal asymptotes. That is just the x-axis. All right, cool. And let's put little arrows on the end here. Okay, so there are a few ways you can go about sort of finding the shape here. I would recommend, how about we put in the y-intercept first. So let's put the y-intercept, which we found was when x is equal to 0 and y is equal to -1/3. So let's say roughly that can be there. And we'll note that in. We'll put 0, -1/3. Okay, and then how about we move that to put that there. And then also we had the idea that when the maximum of the graph of f is when x is equal to 1 and the y coordinate is -1/4. So let's say that is going to be roughly around here. Okay, and we can lob that in. I'm going to zoom in actually to make my life slightly easier. Let's just put this underneath here. 1, -1/4. Okay, cool. So there we have a couple of points that we can use. And then now to get the shape of our curve. Well, we know that the horizontal asymptote is the x-axis. Okay, so that means we're going to have essentially flat lines along here. All right, and x is equal to -1 is a vertical asymptote, and x is equal to 3 is a vertical asymptote. So we're going to have vertical lines running along them. So but that means if I have a horizontal asymptote here and then a vertical asymptote there, that's roughly going to be the shape on the left-hand side for when x is less than -1, because I'm sort of showing that there is an asymptote at the x-axis and a vertical asymptote of x equal -1. We can show that on the other side as well. All right, and so that's going to be like that. And then now for, in the middle, we have, basically our y-intercept and our maximum. So we know we're going to have to run through there, and we have our two vertical asymptotes. Okay, so we're going to need our lines to be running along there. So we essentially sort of have a line here, and a line going through there. And so it's not too hard to then, sort of then assume that the shape of this graph in the middle will be like this. To give my poor drawing, but that will be the graph of f, right? And that, satisfies everything that we need. And we have, we can also, then we might also just put in down the bottom here, horizontal asymptote. That's right underneath. Of y is equal to 0. And then, there you have the answer to question 11a. Okay, on to part B. So we have a function g is defined by gx is equal to 1 over x squared minus 2x minus 3, where x is an element of real numbers and x is greater than 3. Part BR says the inverse of g is g to the power of -1. Okay, and part 1 of part B is show that the inverse of g of x is equal to 1 plus the square root of 4x squared plus x all over x. And part 2 says state the domain of the inverse of g. All right, so let's copy this question. Oh, what have I done? Let's copy this question down to a new page and look at what we've got. Okay. So it's worth noting that g of x is identical to f of x, but the only thing we've changed is the domain, all right? So basically for x is greater than 3, okay? And so if we go back up to our graph and we take that here, let's copy this down. Let's just visualize the bit that we're going to be working with, okay? So the bit of the graph that we're going to need to consider is essentially just this bit here. Okay, so the part that is greater than 3. All right, and so now, in order to find an expression for the inverse, what we tend to do is say, let y equal our function, so g of x. This just makes it easier to rearrange in the following steps. So we can say then y is equal to 1 over x squared minus 2x minus 3. Okay, and then what we actually also what I'm going to note at the same time is the domain and range. Okay, so this is for x is greater than 3, and we can see from our graph up here that when x is greater than 3, then the graph of g is always greater than 0. So that means y is greater than 0 as well. Okay, and so now we swap our x and y's. All right, and so we get x is equal to 1 over y squared minus 2y minus 3. And then now our domain and range have changed. So this is for x is greater than 0 and y is greater than 3. And now we just go about sort of rearranging this equation for y. I'm going to bring the y's over to the left-hand side because generally that's how we write equations. We're going to put y is equal to something. So I'm going to say y squared minus 2y minus 3 is equal to 1 over x. If you're familiar with physics triangles, that's an easy way to rearrange that one there. All right. But yeah, so that's what we've got there. Now, what we can do to this left-hand side is we've got to start making our equation start looking like this. All right. And so the best way to do that is to complete the square. on this left-hand side where we've got the y's, right? And the way we do that is, I think, what would we need to put into brackets and square to get this bit here, to get y squared minus 2y, right? Regardless of what's going to come after that, the constant at the end, we're going to basically account for by subtracting it off of the end as well, okay? So that's going to be y minus 1, all right? And you'll see if you square that out, you times this bracket by itself, you'll get y squared minus 2y, but then you'll get plus 1 on the end, okay? And the way we account for that plus 1 on the end is we just subtract, subtract 1. Yeah, there we go. Subtract 1 minus 3, and then the minus 3 is from that bit there, okay, is equal to 1 over x. We can clean this up a bit and say that this is just y minus 1 squared minus 4 is equal to 1 over x. Now, the next step will be to add 4 to either side, but so that we start getting an expression similar to what we've got here, right, I'm going to put the 4 in front of the 1 over x, all right? It'll make sense in the following steps as to why I did that. So we're going to get y minus 1 squared is equal to 4 plus 1 over x. Okay, now if we essentially now just multiply our right-hand side by x over, just get a similar denominator, get the same denominator on our right-hand side, we can change this to being y minus 1 is equal to 4x squared plus let's say over x squared plus x over x squared. Yeah, we'll do it like that. Okay, and we can, I forgot the squared here. Then we can say that this is y minus 1 squared is equal to 4x squared plus x over x squared. Now we're going to take the square root of both sides, and that's going to give us y minus 1 on the left-hand side is equal to plus and minus the square root of this whole thing. Okay, so 4x squared plus x over x squared. Now, when you take the square root of a fraction, I'm just going to clean up this side bit here. So when you take the square root of a fraction, it's equal to the square root of the numerator over the square root of the denominator. All right, so, and the square root of the denominator here of x squared is just going to be x. And all the thing that is guiding all of my actions here is the fact that I'm trying to work towards this expression here. Okay, and so I can see that this bit here, that's what I'm trying to get to here. All right, so then I can say y minus 1 is equal to, in fact, how about we'll add 1, oh no, we'll do 2 steps here. We'll do 2 steps. So this is equal to the square root of 4x squared plus x over x. Now let's work off to the right here, and what we're going to do is draw a margin, and we'll bring this over, and we'll just copy the same step up to the top here. Okay, and so now what I'm going to do is add 1 to both sides, and same idea, I'm going to put the 1 in front like I did with the 4, so that I get an expression similar to what we have in the question. So we're going to get y is equal to 1 plus and minus the square root, or how about we just copy this down, And since at the start we said that y has to be greater than 3 and x is greater than 0, so let's write that in. Since x is greater than 0 and y is greater than 3, that means we're going to have to reject this negative sign. All right, we're going to have to reject the idea that, because if we had that, then essentially, and knowing that x is greater than 0, that means this whole expression here would give a value of y that is less than 3, which is not allowed. All right, so we're going to have to say then, therefore, y is equal to 1 plus the square root of 4x squared plus x over x. Okay, and that's essentially what we were going for. Now we just need to swap out y and g, or the inverse of g. All right, and we can send there, therefore, g of -1 x is equal to 1 plus square root of 4x squared plus x over x. Okay, on to part 2. Part 2 asks, state the domain of the inverse of g. Okay, so domain of the inverse of a function is equal to the range of that function. So the range of gx is equal to the domain of the inverse of gx. Okay, and so we somewhat sort of noted that here. So that was the range of gx, and so that means the domain of gx is, or the inverse of gx is here, which is x is greater than 0. Okay, so we can note that down here. And we'll say part 2. Okay, domain of g inverse is x is greater than 0. All right, and that is the answer to part 2. We'll put x here. All right, there we go. Okay, on to part C. We have a function h is defined by hx is equal to arctan of x over 2, where x is an element of real numbers. Given that hog of a, or h of g of a is equal to pi over 4, find the value of a. Give your answer in the form p plus q over 2 multiplied by the square root of r, where p, q, and r are elements of positive integers. Okay, tricky one, but we'll what we'll do is we'll take our function g, including its domain. Let's sub that down here. Let's just sort of like make it a bit smaller. All right, and then we'll copy this down to a new page. Copy, let's go down to here, add page. Okay, cool. And so here we have our function. Okay, so first things first, I reckon a good idea would be to get an expression for h of g of a, or hog of a, if you, or sorry, of x. So h of g of x. So if we go through and we find that, let's go. So h of g of x. Okay. Now this is going to be essentially just where we substitute in the function of g as our x term into a function of h. All right. So that's going to look a little like this. So that's going to equal arc tan of 1 over x squared minus 2x minus 3, and then that's all over 2. All right, and then we can clean this up a little bit. And, oh, what have I done? We've got, that's right. Yeah, we can get rid of that. We can go like that. All right, cool. So we can clean this up a bit and call it arctan of 1 over 2 multiplied by the denominator, so x squared minus 2x minus 3. Cool, and then now we have an expression for essentially whole of x or h of g of x. All right, we know that h of g of a is equal to pi over 4. All right, so now let's show that. So we can go h of g of a is going to equal arctan of 1 over 2 lots of a squared minus 2a minus 3. Cool. And then close bracket. All right. And we know that this is equal to pi over 4. All right. So now if we go to our, let's bring in one of the exact value triangles. One with pi over 4. And we can see here that, in fact, we'll write it over here. We can see that tan over 4, or tan of pi over 4. Let's just make this slightly thinner. Rewrite that. So let's just say tan of pi over 4 is going to equal 1. Okay, so then that basically means, therefore, arctan of 1 will equal pi over 4. All right, so therefore we can sort of use that information there and say that our expression in here, this expression here, that's going to have to equal 1. All right, so let's put a green underline and we'll say this is going to have to equal 1. All right, and we'll bring that down. So we'll say, therefore, 1 over 2 multiplied by a squared minus 2a minus 3 is going to have to equal 1. Now we'll bring the 1 over to the other side. And so we're going to say that 2 multiplied by a squared minus 2a minus 3 is going to essentially equal 1 over 1, which will just be 1. All right, and then now we can, let's make this equation equal to 0. So then we will have a quadratic equation. And so we're going to get 2a squared minus 4a minus 6, and then also minus 1, because we're going to bring that over to the other side. So it's going to be minus 7 is equal to 0. And then now, yeah, we have a quadratic equation where we can use the quadratic formula, which is as follows. We'll bring this over here. So quadratic formula is x is equal to negative b plus and minus the square root of b squared minus 4ac over 2a, where b is the coefficient of the h to the power 1 term, or a to the power of 1 term in our example here. A is the coefficient of the x squared term, and c is the constant on the end. So we can do that. So we've got a is equal to negative 4, which is just going to be 4. Okay, plus and minus the square root of negative 4 squared, which is essentially just the same as 4 squared, but I'll write it in, minus 4 times by a, which is 2, times by c, which is negative 7. All right, cool. And then that's all divided by 2 lots of a, which is 2 times 2. All right, cool. Now we can clean this up a bit. And so let's go ahead and do that. We'll say 4 plus and minus the square root of 16. This is going to end up being plus 56, I believe. Yeah, 56. 6. Okay, all over 4. And then we can also clean this up a bit. What we'll do is we'll draw a margin down here, and we'll work off to the right-hand side here. Okay, and we'll copy the same step. All right, and so we have a value of 16 plus 56, which will give me 72. And so I can call this here. Yeah, A is equal to 4 plus and minus the square root of 72 all over 4. And now what we can do is separate this into two separate fractions, if you will. So we could say we'd get 4 over 4 plus and minus the square root of 72 over 4. Now, 4 over 4 is just going to be 1. So we can say A is equal to 1 plus and minus the square root of 72 over 4. Now we can basically break down the square root of 72 by thinking of its squared factors, I like to call it. So basically numbers that go into 72. So the first one that comes to mind is 36. So 36 is 6 squared. So and 36 times 2 is 72. So in fact, let me just write that in. There's going to be 1 plus and minus the square root of 36 times 2 over 4. Okay, so that's going to be the same as writing 1 plus and minus 6 root 2 over 4. And we can simplify the 4 and the 6 to be 3 and 2. Divide them both by 2. And so we get 1 plus and minus the square root of, 3 multiplied by the square root of 2 over 2. Now, we might be wondering now, how do we find the value of A? And we have to go up again and see that we had g of x was part of our function here. And g of x is only valid for values of x that are greater than 3. Okay, so therefore that means A has to be greater than 3. And so therefore A must be greater than 3. And so if we're starting with 1 and then subtracting something, we could never be greater than 3. So we have to basically take the positive version of the right-hand side. So therefore A is greater than 3. And so A is equal to 1 plus 3 over 2 multiplied by the square root of 2. And that is the answer to part C. Question 12. In the following Argand diagram, the points Z1, O, or the origin, and Z2 are the vertices of triangle Z1, O, the origin, and Z2, described anti-clockwise. Right. Cool, and we got the Argand diagram there. Very nice. The point Z1 represents a complex number. Z1 is equal to R1 e to the power of I alpha, where R1 is greater than 0. Point Z2 represents the complex number. Z2 is equal to R2 e to the power of I theta, where R2 is greater than 0. Angles alpha and theta are measured anti-clockwise from the positive direction of the real axis, such that 0 is less than or equal to alpha, theta is less than 2 pi, and alpha minus theta lies between 0 and pi radians. Part A asks, show that Z1 and Z1 multiplied by Z2, or the complex conjugate of Z2, is equal to R1 multiplied by R2 e to the power of I of alpha minus theta. Cool. Right, let's take a whole bunch of this information down. We will, in fact, yeah, we'll take all of this. We'll bring this all down. Okay. Let's go, yeah, new page. Oh yeah, we'll add one there. Okay, so when you take the complex conjugate of a, how's that going to look now? We'll make it a bit bigger. Okay, when you take the complex conjugate of a complex number, all right, all you do is you change so the real part stays the same, and the imaginary part becomes or changes sign or becomes negative. Okay, so for example, if we were to call, if this imaginary part here was, let's say, equal to x, all right, then that means what would happen is Z2 star would be coming down here. We'll say Z2 star, and then that would be equal to x as well, all right, or negative x if you come down, but the length would be the same, right? And that line should be straight. I know it's somewhat, let's just see if we duplicate that and bring it down. Yeah, somewhat okay. All right, so it just comes down, right? And then equally, we could say that then, therefore, this angle in here is equal to negative theta, all right? And so, and we'll call this, we'll call this negative x. Okay, so the main gist is just to remember that when you when you take the complex conjugate of a complex number, the only thing that changes is the imaginary part. Okay, so therefore we can sort of say up here, therefore Z2 star is going to equal R to e to the power of I negative I theta. Sorry, that's in fact, we'll just put it in here in brackets. Negative theta, which we could also call negative I theta, if you will. All right, yeah, how about we do that? We'll go R2 e to the power of negative I theta. All right, and we're asked to show in part A that Z1 times by Z2 star is going to be R1, R2, e to the power of I of alpha minus theta. Well, Z1, let's just bring this down here. So Z1 times by Z2 star is going to equal our Z1, which is R1 e to the power of I alpha. Then I'm just going to draw as A because I'm terrible at writing that symbol. In fact, we can make it a little bit better. Now we'll just stick with A. All right. Multiplied by R2 e negative I theta. Okay, so if you're not familiar with the operations of complex numbers or how we do them, so when they are in this form, the exponential form, all we need to do is take the sum of the arguments and the product of the moduli and moduluses. Okay, so then this is going to equal R1, R2 multiplied by e to the power of I alpha minus I theta. Now, in our power here, we have a common factor of I, so we can factorize that out, and so we can say R1 multiplied by R2 is going to be equal to e to the power of I of A alpha minus theta. Right, and there we have, as required, the answer. And that is the answer to part A. Okay, I just rearranged or reshuffled part A here, just over to the right-hand side. And now let's go into part B. Okay, so part B asks, given that the real part of Z1 times Z2 star is equal to 0, show that Z1, the origin, and Z2 is a right-angled triangle. Okay, let's just bring this over here, there. Let's plonk this down here. Okay, let's make that a bit bigger. All right, nice. So part B says, so if the real part is equal to 0, let's just go get our, let's go bring down our diagram of what we have. If they're saying that the real part is equal to 0, that means our, Z1 times Z star is going to have to lie on the imaginary axis. Right? It's going to have to lie somewhere along there. Okay, which would mean then the argument of Z1 times Z star will have to be plus and minus the square root, or sorry, plus and minus pi over 2. Beg your pardon. All right, so let's jot that down. So given that we have the real part of Z1, Z2 star is equal to 0 means, oh, that's a bit annoying. Let's see if I can do that. All right, no, we'll leave it there. Means we can then sort of conclude that that means the argument of Z1, Z2 star, which we found up the top here, is alpha minus theta. So we can put that in, is equal to alpha minus theta, has to equal plus and minus pi over 2. So equal, yeah, there we go. All right, and so since we are told in the question here, we're told that alpha minus theta is equal to pi. Oh, sorry, alpha minus theta lies between 0 and pi, so therefore it'd have to be positive. So therefore we can sort of conclude that alpha minus theta will have to equal pi over 2. And we can see that that is going to be this angle in here, okay? This one here. There, because we've got alpha as this big angle here, and theta, let's use some different colors here. So we've got alpha as this there, and then theta is just that there. So that means this angle in here is going to have to be alpha minus theta, all right? And we've just shown that alpha minus theta has to equal, pi over 2, given that the real part of Z1 times Z2 star is equal to 0. All right, and so then therefore we can sort of conclude that the angle of Z1, O, and Z2 will equal pi over 2, and hence we'll write hence. In fact, let's bring this. No, that's not going to work. All right, hence we'll take this is a right angle triangle. Angled triangle. Right, and that is the answer to part B. Okay, on to part C. So, in part C, D, and E, consider the case where Z1, O, and Z2 is an equilateral triangle. Part C1 asks, express Z1 in terms of Z2. And part 2 says, hence show that Z1 squared plus Z2 squared is equal to Z1 times by Z2. Okay, cool. Let's copy this down, and we might be, may use a new, we'll do this on a new page. Right, cool. There we go. That's that. All right, and then let's also take down all this, our diagram with a whole bunch, all the information that we need. Okay, and so this question basically requires you to show an understanding of, let's go at this. All right. Understanding of what an equilateral triangle is, essentially, okay? So an equilateral triangle has sides all being the same, and the angles within the equilateral triangle all are pi over 3. They're all 60 degrees, but yeah, pi over 3. Okay, so we need to express Z1 in terms of Z2, all right? So that means if we go into here and we go into our diagram again, the angle within our, this angle here, which we found was, alpha minus theta, this is going to have to equal pi over 3, all right? Equally, right, so also we're going to have to say that R1 and R2 are the same, okay, because all the sides are going to have to be the same. So that's a couple of things we can sort of note. So we're going to have to say alpha minus theta equal pi over 3, as I just said, and then also R1 is going to have to equal R2. And so now with this information here, we can now write R1, or, actually what we could also do is now write theta in terms of, or alpha in terms of theta and pi over 3. So how about we do that? We'll say, therefore, alpha is equal to theta plus pi over 3. All right. And so now we can write Z1 in terms of, yeah, that's what we're going to do. So express Z1 in terms of Z2. All right. So if we bring this down, let's, yeah, we can go over here. We'll go. So in fact, let's put a little CI up here. All right. So then, therefore, Z1 is going to equal, well, R2 is the same as R1. So we can put that there. All right. The moduli are going to have to be the same. And now the argument for Z1 we can represent as theta plus pi over 3. So we can go is equal to theta plus pi over 3. Let me rewrite that, pi over 3. Let's go a little bit up. All right, cool. And so now we can expand the bracket within up the top here. So in the power of E, and we could sort of say that this is then Z1 to R2 E I theta plus I pi over 3. Okay. Now we can use the indice law that states that sort of, how about, yeah, we'll do it here, where if you've got a to the power of m times by a to the power of n, this is equal to a to the power of m plus n. Okay, so we can use what we've got here, and in fact, let's we can use what we've got and separate out the power of e into two separate entities. And so we could say that then Z1 is equal to R2 multiplied by E I theta plus E to the power of I pi over 3. Okay. And then now we have something that, looks like this here. This here looks like Z2, this bit. This is Z2. Okay. And also I put plus there, that's meant to be times, beg your pardon. Okay, that's meant to be times in there. Okay, so we've got Z2 then times by E to the power of I of pi over 3. And so then we can conclude, we'll bring this down here and we'll put this C per I. So therefore, Z1 is equal to Z2 E I to the power of pi over 3. And now that is an expression for Z1 in terms of Z2 as required, and that is the answer to part C1. Okay, on to part C2. Hence show that Z1 squared plus Z2 squared is equal to Z1 multiplied by Z2. So if we start with the right-hand side of this equation and have a look, and we go Z1 times by Z2. Well, we found an expression for Z1 in terms of Z2, literally just above here. So we can use that. So we can say, in fact, it might even be, let's bring this down slightly so there's a bit of a gap. We can bring this as an expression for Z1, lob it into brackets, then multiply by Z2. Okay, and then there we have, an expression for Z1 multiplied by Z2, all in terms of Z2. And if we want to clean this up, we could end up calling it that it is e to the power of I pi over 3 multiplied by Z2 squared. All right, cool. So there is an expression for the right-hand side. And now we've got to essentially best find an expression for the left-hand, or show that the left-hand side can be expressed in the same way. All right, so let's look at that now. So we'll go Z1 squared plus Z2 squared. Now this is going to be equal to, so now we're going to use the same expression that we had for Z1 in terms of Z2. So let's lob that in. So we're going to have Z2 multiplied by E to the power of I of pi over 3. Let's make that square bracket slightly nicer. squared plus Z2 squared. Okay, so that starts us off quite nicely. Now, when we square this whole term here, what we're going to do is we're going to get Z2, let's make that a bit nicer, Z2 squared, and then we're going to have to multiply the argument by 2. Okay, so that's going to be EI to the power of 2 pi over 3 plus Z2 squared. Okay, so that is a good start. Now, what we're going to have to do is a bit of well, first of all, let's take out the common factor between these two, which is Z2 squared. So let's just put let's go with EI 2 pi over 3 plus 1 and then Z2 squared. All right, so we're going to have to somehow show that this is equal to this, okay? And we'll show that graphically. Okay, well, not graphic, on an Argand diagram. So if we do this and then say this is equal to pi over 3. Now come over to the right hand. Let's go over to the right hand side and let's look at this visually. So, and we'll take there, and this is the imaginary axis. This is the real axis here. And so this complex number here, e to the power of I of 2 pi over 3, is a complex number with a modulus of 1. We don't write the 1 in here, but you could put a 1 in there. And it has an argument of 2 pi over 3. All right, which will be something like this line here. Okay, and so we can call this e to the power of I pi, 2 pi over 3, beg your pardon, 2 pi over 3, where this angle here is 2 pi, and actually, hold on, let me just make this a little smaller and put this over here. Where this angle here is 2 pi over 3. All right, now, when we add 1 to this complex number, that's going to give us one that comes over here. All right, and now we can see we have an equilateral triangle with sides equal to 1. So let's say this is equal to 1. This is equal to 1. It's not perfect, is it? It'd be probably slightly better visually if I bring this out. It's slightly better, but still not perfect. Now, if we have a look at the triangle that is created on the left-hand side in terms of a blue side, in purple, beg your pardon, we can sort of see that we're going to end up getting a right-angled triangle that has the same angles as one of our exact value triangles, which I'll bring over, just here. Okay, so we're going to need to use this exact value triangle. Is that all right there? Yeah, okay, cool. So we have, if this is 2 pi over 3, this purple one here, then that means this angle in here, and in fact, let's change these colors so they're easier to differentiate. Okay, so that means the base, if the hypotenuse is, 1 in our case here, but it's 2 in the exact value triangle that we learned, that means the base of this triangle is going to be -0.5. Okay, and that means this side here, so the long side that is not the hypotenuse, okay, is going to be √3/2. Right, so we can put that there. We don't really need to know all of that, but what we do essentially need to see is that when we add 1 to this triangle here, because here this angle in here, this will be pi over 3. That means when we add 1, we're going to get sort of a half here, and then a half here as well. All right, with the length of this side here being 1. All right, and then the height of this will be the same, and the argument within here will just be pi over 3. as well. Okay, so that's essentially showing graphically on an argand diagram that this complex number here, this is just e to the power of I pi over 3, which is what we needed to show. We needed to show that when we add 1 to e to the power of I of 2, so e to the power of I times 2 pi over 3 plus 1 is the same as e to the power of I of pi over 3, as we have somewhat shown here, okay? And so then therefore we can conclude that this is equal to e to the power of I pi over 3 multiplied by z2 squared, which is the same as we had here. So then we can say, therefore, what was our z1 squared plus z2 squared is equal to z1 multiplied by z2. Now that is the answer to part C2. Okay, on to part D and E that I have copied down here. So first of all, with part D, so let Z1 and Z2 be the distinct roots of the equation Z squared plus AZ plus B equal to 0, where Z is an element of the complex number set and A and B are elements of real numbers. Part D says, use a result from part C2 to show that A squared minus 3B equals 0. Right, so we're going to need some formulae from the formula booklet. Let's go over and have a look there. So it's in the topic 2 HL only section. That's topic 3, sorry. Here, so this one here. Okay, so the sum and product of the roots of the polynomial equations of the form here. Okay, so bring this over. Let's lob this down here. Okay, so for D, what we're going to have to note is, so n represents the degree of the polynomial we have here. So n is going to equal 2. AO is the constant term in our polynomial, which is up here. Okay, so that's B. A1 is the coefficient of the Z term. Okay, and that's just A. And A2 is the coefficient of the Z squared term, beg your pardon, sorry, which is 1. Okay, so then now we can sort of just lob these into our formulae. So the sum, or we could sum, let me sort that out, is going to be equal to negative of an minus 1. So negative a, essentially, we need this one here. Okay, so with n being 2. So negative a over an, which is the degree of the polynomial, so a2, which is this one here, which is what? Over 1. Okay, so the sum is equal to negative a. Now let's, on the same line, let's find the product. Okay, and this is going to be equal to negative 1 to the power of n, where n is 2, multiplied by AO, which is B, okay? And then divided by, AN, which is going to be 1. Oops, sorry. Okay, now moving on, and so yeah, I probably should have put this in. So therefore, Z1 plus Z2 is equal to negative A, and Z1 multiplied by Z2 is equal to B, just by itself. All right, so there we have a couple of useful things that we can use. Okay, so going back to part C2, we showed that Z1 squared plus Z2 squared is equal to Z1 multiplied by Z2. Okay, so it's, in fact, let's put that in from C2. Z1, wait, hold on, let me just, Z1 squared plus Z2 squared, yeah, Z1 squared plus Z2 squared is equal to Z1, Z2, okay? Now, if we take Z1 plus Z2 and square it. All right, so if we go here and we go Z1 plus Z2 squared, what we're going to end up getting is Z1 squared plus Z2 squared plus 2 lots of Z1 multiplied by Z2. That kind of comes from you can, just basically a binomial, where if you have A plus B squared, this is equal to A squared plus B squared plus 2AB. And let's just bring that down to be on the same line. Big pardon for my handwriting towards the end there, but I hope you can read that. Okay, so that's the idea there. Okay, now we've got this bit here, which is the sum, all right? And then we've got this bit here, which we know is equal to B. And we've also got this bit here. So in fact, let's go through. This is just going to be effectively negative A squared. This here, from above, we know that that's just Z1, Z2. So this is equal to Z1, Z2, which is equal to B, all right? And then we have here, this bit here is 2 times Z1 times Z2, which is just going to be equal to 2B. All right, and so if we bring this all down, we've got negative A squared is equal to B plus 2B. Now, negative A squared is just going to be A squared. So A squared is equal to B plus 2B, which is going to be 3B. Okay, and then we don't need a new line. We can just bring this over here. And so then therefore, as required, A squared minus 3B is equal to 0. And that is the answer to part D. Consider the equation z squared plus az plus 12 is equal to 0, where z is an element of complex numbers and a is an element of real numbers. Given that alpha minus theta lies between 0 and pi radians, deduce that only one equilateral triangle, Z1, O, Z2, can be formed from the point O and the roots of this equation. Okay, lovely. Now, what we're going to do is actually, let's bring just that down to here. We're going to end up needing some more pages, but yeah, we'll just do that then there. All right, cool. Okay, so then essentially in this part here, if we use what we've sort of found in part E, all right, essentially what we've got is B has now turned into 12, all right? And if we use the bit of information that we're told, a squared minus 3b has to be equal to 0, then we can sort of say then, b is equal to 12. So therefore, a squared minus 3 lots of 12 have to equal 0, which is the same as saying, in fact, it's, we'll bring it down here. Just say, same as saying a squared minus 36 is equal to 0. And so then therefore, a will have to equal plus and minus 6. Okay. And so then now to find the roots of the possible roots of this equation, we're going to have to use the quadratic formula, which is as follows. X is equal to negative b plus and minus the square root of b squared minus 4ac all over 2a. Now, don't get confused with the idea that we have similar letters sort of crossing paths here, okay? This is just the general formula for the quadratic formula. And so a actually in this circumstance is going to be b, all right? So if we go and apply this, we can bring this over and let's bring this over. Let's say then z is going to equal, in fact, let's put this in. So negative a plus and minus the square root. In fact, now how about we'll put in what a is, what we've just found, so it's -6, plus and minus 6. So since we've got to put negative b, why don't we do this idea of doing minus plus 6? Just shows that you've acknowledged that there's a negative sign in front of there. Plus and minus the square root of a squared, which is plus or minus 6 squared, which will be 36. All right. Let's put that in. All right. Minus 4 times a, where in this example here, let's write in here. So a is going to be equal to 1, b is going to be equal to a, and c is going to be equal to 12. Just going off our quadratic up here. Okay, so this is going to be equal to 4. Oh, what have I done? Wrong color. And get rid of that. 4 times by 1 times by 12 all over 2 lots of a, which is just going to be 2 lots of 1, which is just a. Now, if we go and clean this up, we're going to get negative and plus 6 plus and minus the square root of, this is 36 minus, so 4 times 1 times 12 is 48. So it'd be 36 minus 48, which will give us 12, negative 12, beg your pardon. So negative 12 over 2. Okay, now let's go to a new page, and actually let's just copy this down. Okay, and so if we wanted to clean this up a little bit, we can separate out the square root of negative 2. In fact, I'll write this all out, actually. Let's just put this all out. So negative plus 6 over 2 plus and minus the square root of, so we can change this to being 4 times by 3 times by I squared. Okay, because I squared is equal to -1. Now that's over 2. Now the square root of 4 is going to be 2. So we can effectively just cancel out these guys here. And we will get a -6, negative plus minus 6, whatever, can cancel out with the 2 as well. And that's just going to become 3, right? And so then we can conclude that z is going to be negative and plus 3 plus and minus the square root of 3i. Okay, but now we have to, so this gives 4 possible roots to this equation. All right, we've got the idea where we do -3 plus the square root of 3i, -3 minus the square root of 3i, then 3 plus the square root of 3i, and 3 minus the square root of 3i. So we could even just note that on a whole bunch of Argand diagrams. All right, so how about we just take this, actually, rather than trying to fit them off to the side there, let's just let's make a whole bunch of these and bring this over to here. Okay, so what have I done? So let's do, so what would be, so if we somewhat looked at the first one, let's say Z1 is the first option I said, so -3 plus the square root of 3i. Well, that's going to be something that comes off somewhat like that, okay? It doesn't have to be perfect. And then the next one, so we need to have the one which will have an internal angle of pi/3 between the two complex numbers, because these need to form an equilateral triangle. And so that would be this one down here. We can say that this is Z1, this is Z2, okay? And then that's going to be, let's bring these down so we have a bit of working, all right? And that means this internal angle in here is pi/3, which we need, okay? Where Z1, this is going to be, in fact, let's write the whole thing in. In fact, let's just get rid of this. So this is going to be where Z1 is equal to -3 plus √3i. And then this one is going to be where Z2 is equal to -3 plus hold on, the square root of 3i. Okay, Now, the other option would be when we have, let's say, positive 3 plus and minus the square root of 3i. So positive 3 plus the square root of 3i. So we can call that there. So this is going to be z1 is equal to positive 3 plus and plus the square root of 3i. And then the corresponding one for z2 would have to be z2 is equal to 3 minus the square root of 3i. And then we end up having, this, we could have the exact same idea here, where z1 and z2 swapped over. But we're going to have to do this fucking again. So essentially what we need to do is find the pair of roots that we have here that will have a angle between them of pi over 3, because we need this to satisfy the fact that they, z1, o, and z2 make an equilateral triangle. We need to find the pair of roots that satisfy this equation up here. Okay, so let's just bring that down. All right, so we need to find the pair that satisfy this here. Okay, so if we consider a few Argand diagrams and let's bring that there, that needs to be straight. Okay, and we'll have imaginary there, we'll have real here. So first of all, we could go with the idea of -3. All right, so we could go with -3. Let's just say that's like we got plus, we'll go -3 plus 3i, so that could be z1 there is equal to -3 plus, root 3i. Then we could also have down here, this could be z2 is equal to -3 plus root 3i. Okay, then alternatively we could have pretty much the same Argand diagram, but z2 and z1 swap over. Okay, which doesn't change a lot in terms of the visual, but it will impact this requirement we have over here. So let's I'll just write in. So that could be z2 over there. And then alternatively, if we just we'll take this. In fact, we'll take the imaginary real part as well. Bring this over to here. Let's get rid of this. And we'll have the pairs of when we're using the positive 3. So 3 in the real, 3 units in the real direction. So that could be there. We could call this z1 is equal to 3 plus root 3i. And then we could have this one down here being z2 is equal to 3 minus root 3i. And then same idea again. We bring this down. Okay, and bring this down, but swap over these. Swap z1 and z2. Okay, lovely. All right, there we go. And then the angle between each of all of these is pi over 3, which I am going to note as well. All right, so this angle is pi over 3. This angle is pi over 3. This angle is pi over 3, and so on. Okay, they're not drawn to scale, but you get the idea. Okay, so going back to the question. Okay, so where do we have our z? So the argument of z1 is alpha, all right? The argument of z2 is theta. Okay, so we could even just lob that down here. So we've got arg z1 subtract arg z2. And we need this to be greater than 0, so positive. And also we need it to be less than pi. Now, if we go through our different possibilities, if we look at the one on the left here, okay, so top left, we've got z1. The argument of z1 is going to be coming around all the way over here. Okay, so that's going to be 2 pi over 3, but we can instantly see that the theta, so the argument of z2, is going to be greater than the argument of z1. So that means we can sort of conclude for this guy here. Let's go alpha minus theta. This is going to be less than 0. So that's no good. That's no bueno. If we go over now to the one on the right hand side, we can say, if we look at this one here, we've got z1 is going to be essentially just pi over 6, and then z2 is going to be a very large value. All right, so z2 is going to be coming all the way around here. Okay, so that's going to be less than 0 again. So alpha minus theta will be less than 0. Okay, and then if we go down to this one here, z1 is going to come all the way around here. So be large. That's going to be essentially 11 pi over 6. Okay, and then z2 is just going to be pi over 6, which will give us then, so the difference between them will be 10 pi over 6, which is greater than pi. So for this one here, we have alpha minus theta is greater than, pi, which is no good. But then we look at our last possibility here, and we've got z1 being all the way round to here. So what's that? Pi plus pi over 6, okay? Then subtract 2 pi over 3. And rather than doing the maths, we can figure out that, in fact, we can do it. We'll go, so z1, this is going to be alpha minus theta is going to equal 7 pi over 6. Subtract effectively, what we got here, 5 pi over 5 pi over 6. Is equal to 2 pi over 6, or just pi over 3, which is within our acceptable range. And so that's essentially what we needed to find. So that's the pair. Okay, so we could then go ahead and conclude, there are 4 possible equilateral triangles. That can be formed, I suppose we could say, such that the from the origin and the roots, and satisfy the equation z squared plus az plus 12 is equal to 0. 4 possible equilateral that can be formed. That can be formed. Let's say they're formed, but only one such that 0 is less than alpha minus theta, which is less than pi. Cool. And then that is the answer to part 12E.